Hello there, and welcome to the Cosmographer. Physics can predict one property of the electron and then measure it, and the two agree to one part in a million. That same body of physics says the electron has no size at all, that you have never touched anything, not once, and that the present moment is not moving. Tonight's list has 10 entries, and every one of them is published work. Number 8 is a letter Einstein wrote to a grieving family 4 weeks before his own death. Number 5 is an experiment in which the measurement settings were chosen by light that left 2 quasars before the solar system existed. And number 4 is a fit to 50 million pixels of the oldest light in the universe, from a model in which everything inside is written on a surface. The entries are not ranked by how likely they are. They are ranked by one rule: how much of reality each one takes away. Get comfortable and settle in. If you enjoy falling asleep to careful arguments about difficult questions, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, after 10 things have been removed, the universe will have carried on behaving exactly as before, and that turns out to be the point. Let's begin at number 10. Number 10. The senses were never built to show you the world. There are 10 reasons on tonight's list, and every one of them is a piece of published work. Some are proved theorems. Some are completed experiments with numbers attached. Some are formal arguments that appear in peer-reviewed journals and are argued over by people who do this for a living. None of them are internet folklore, and none of them will be stated tonight with more confidence than the evidence actually carries. They are not ranked by how likely they are to be true. They are ranked by one rule, and the rule is worth holding on to for the next 3 hours. Each entry is ranked by how much of reality it takes away. Number 10 takes away the least. It removes only the reliability of your senses, and it leaves everything else standing. Number 9 takes away the solidity of matter. After that, the list keeps going, and each entry removes one more thing that the entry before it had left in place. The flow of time, the smoothness of space, the existence of facts that are true for everybody, the idea that objects have properties before anyone looks at them, depth, distance, your own standing as an ordinary person with a real past, and at number 1, the base level of reality itself. That is the ladder. 10 steps down, each one deeper than the last, and by the end of it, something quite unexpected happens, which we will come back to at the very bottom. So, we begin with the shallowest cut on the list, and it starts with a question that sounds simple. What are your eyes for? The obvious answer is that they are for seeing the world. That answer is almost certainly wrong, and the argument against it is not a philosophical mood. It is a theorem. The work belongs to Donald Hoffman, a cognitive scientist at the University of California, Irvine, and it goes under the name of the interface theory of perception. Its central claim is narrower and more precise than the popular versions of it suggest. It does not say that nothing exists. It says that perception evolved to guide useful behavior, not to report the structure of the world, and that the format of your experience is therefore not the format of what is out there. The formal backbone is called the fitness beats truth theorem. It was proved by Chetan Prakash, Kyle Stevens, Donald Hoffman, Manish Singh and Chris Fields, and published in the journal Acta Biotheoretica in 2021. Using evolutionary game theory and Bayesian decision theory, the theorem shows that an organism whose perceptions track only fitness payoffs will consistently outcompete an organism whose perceptions track the actual state of the world. That result on its own would be interesting. What makes it uncomfortable is the direction it runs. The advantage of the fitness-only strategy grows with the size of the perceptual space. The richer and more detailed the world an organism could in principle perceive, the more strongly natural selection favors the organism that does not bother trying. The supporting evidence comes from evolutionary game simulations and genetic algorithms in which two kinds of virtual creature are set loose in the same environment. One perceives the truth about resource quantities. The other perceives only a compressed signal about what will keep it alive. In the great majority of the environments modeled, the truth-seeing creatures go extinct. Hoffman's own analogy for this is the desktop of a computer. A file icon is blue, it is rectangular, and it sits in the lower right corner of the screen. Not one of those three properties describes the file. There is nothing blue inside the machine, nothing rectangular, and nothing in a corner. The interface is useful precisely because it hides the voltages, rather than reporting them. If you had to see the transistors to write a letter, you would never write a letter. The best documented real-world illustration of the same principle involves a beetle and a beer bottle. Somewhere on a roadside in Western Australia, in the late afternoon, a male jewel beetle of the species Julodomorpha bakewelli lifts off and begins to search. He is a large insect, heavy in flight, and he is looking for a female. His visual system has been tuned by a very long stretch of evolutionary time to detect four things at once: large, brown, shiny, dimpled. Four cheap cues, and if all four arrive together, the answer is a female, and the answer has been reliable for as long as there have been beetles. He finds all four. He lands. What he has landed on is a discarded beer bottle, a squat brown stubby lying in the dust with the sun catching its base, and the small raised bumps around its lower edge catching it more brightly still. The bottle is larger than any female he could ever meet. It is browner and shinier, and its dimples are more regular than any real beetle's. On every axis his visual system measures, the bottle is a better female than a female. He does not leave. Other males land beside him. Ants arrive and begin, slowly, to eat him while he stays exactly where he is. That work was published by Darrell Gwynn and David Rentz in the early 1980s, and it received an Ig Nobel Prize in 2011. The beetle is not malfunctioning. He is doing precisely what he evolved to do, at maximum efficiency, on an object that his interface was never designed to distinguish. Now hold the beetle in mind and look at the machinery you are using to read this. The human retina carries roughly 130 million photoreceptors. The optic nerve leaving each eye carries roughly 1 million fibers. Something like 100 to 1 of the incoming data is thrown away before the signal has left the eyeball. 100 million receptors, reduced to 1 million fibers. That number is worth remembering, because it will return much later in this list, in a place you would not expect, and it will be doing a very different job. The compression is not the only editing. Each optic nerve leaves the eye through a patch of retina that has no photoreceptors on it at all, about 5 degrees across. There is a hole in each of your visual fields, and it is not small. You do not see a hole. The brain fills it with content that it invents, based on whatever surrounds it. Edme Mariotte discovered this in 1660 and demonstrated it as entertainment at the court of Charles II by positioning courtiers so that their heads disappeared. Your eyes also jump. They make roughly 3 saccades every second, on the order of 150,000 of them in a waking day, and vision is actively suppressed during each jump so that the world does not smear. What feels like a continuous visual field is stitched together from something much closer to a slideshow, with the gaps papered over so smoothly that most people go their entire lives without noticing. Then there is the delay. Light landing on the retina takes something like 70 to 100 milliseconds to produce activity in the visual cortex. Everything you see, you are seeing about 1/10 of a second late. The brain compensates by extrapolating forward, guessing where a moving thing will be by the time the signal lands, and that guess is measurable. It shows up as the flash lag effect, in which a moving object is perceived slightly ahead of where it actually is. And the editing extends to whether you notice changes at all. In an experiment run by Daniel Simons and Daniel Levin in 1998, an experimenter stopped pedestrians to ask for directions. Mid-conversation, 2 workers carried a door between the 2 people, and behind the door the experimenter was swapped for a different person, wearing different clothes. Roughly half the pedestrians carried on giving directions without noticing that they were now talking to a stranger. Color is perhaps the cleanest case of all, because color is not out there. Wavelength is out there. Color is something your nervous system constructs, and the proof is a phenomenon called metamerism, 2 entirely different mixtures of wavelengths, with nothing in common physically, can produce percepts that are indistinguishable. In 2015, a photograph of a dress divided the internet into 2 populations who saw different colors in the same pixels, because their brains made different assumptions about the light that had fallen on it. The bandwidth is narrow as well. Human vision runs from roughly 380 to 700 nanometers. That is 1 octave of an electromagnetic spectrum that our instruments now cover across more than 20 octaves. Radio, microwave, infrared, ultraviolet, X-rays, gamma rays. All of it is arriving. 1 octave gets through. It would be reasonable to assume that more sensors would mean more truth. The mantis shrimp is the standard test of that assumption because it has 12 to 16 classes of photoreceptor to R3. When Hannah Thorne and colleagues actually tested the animal's color discrimination and published the results in the journal Science in 2014, they found that mantis shrimp discriminate colors worse than humans do. The extra channels do not buy fidelity. They buy speed. It is a fast readout for an animal that has to make a decision in milliseconds, which is exactly what the theorem predicts an interface would be. There is one more piece of anatomy that makes the point sharper than any of the illusions. Hermann von Helmholtz proposed in 1867 that perception is unconscious inference. The brain guesses, and the senses correct the guess. Modern anatomy supports him rather starkly. The nerve fibers running from the cortex back down to the lateral geniculate nucleus, the relay station in the middle of the brain, outnumber the fibers arriving from the eye by something like 10 to 1. Most of the traffic on that route is going the wrong way. The eye is not sending you a picture. The brain is generating a picture, and the eye is sending back corrections. Vision is only the most obvious case, and every other sense tells the same story. Sound is not in the world either. Pressure waves are in the world. Pitch, timbre, and the sense of a note are constructed, and the clearest demonstration is the missing fundamental, in which a set of higher harmonics with the bass tone physically removed still produces the clear perception of that bass tone. The brain supplies a note that is not present in the air. Body ownership is constructed too, and it can be moved. In 1998, Matthew Botvinnik and Jonathan Cohen showed that if a rubber hand is placed on a table in front of a person while their real hand is hidden, and both are stroked with a brush at the same moment, most people begin to feel the touch in the rubber hand within about a minute. Sight and touch agree, and the brain accepts the object as part of the body, because agreement is the only evidence it ever has. The senses also overrule one another without asking. The McGurk effect takes a recording of one syllable and pairs it with video of a mouth forming a different one, and what a listener hears is a third syllable that nobody said. Vision wins, and the loss is invisible from the inside. Even the order of events is negotiable. The brain resequences signals within a window of roughly 80 milliseconds in order to produce the causal story it expects, which means the order in which things seem to happen is partly a decision. And when the two eyes are given genuinely conflicting images, the result is not a blend. It is binocular rivalry, in which awareness flips back and forth between one image and the other, because the system will produce a single coherent account or none at all. The last piece of context is that other interfaces exist, and they are documented. Bees and hummingbirds see ultraviolet nectar guides on petals, patterns that function as landing marks and are entirely invisible to us. Pit vipers form thermal images of warm bodies in complete darkness. Weakly electric fish generate a field around themselves and build a working model of their surroundings from the distortions in water too murky for eyes to be useful at all. Each of those animals is looking at the same room you are, and each of them is receiving a different summary. One estimate of the bandwidth of conscious visual experience puts it at a few tens of bits per second, against a raw retinal input on the order of 10 million bits per second. Whatever is arriving, almost none of it is reaching you. Now, the honest counterweight, because this list gives one to every entry that deserves it. The interface theory has serious critics, and their objection is a good one. For many tasks, seeing the truth is simply the cheapest way to survive. An animal that perceives the cliff edge accurately does better than one running some lossy proxy for cliff edges, and the theorem's model of perception as a pure payoff tracking channel may not describe how real nervous systems are built. Whether the fitness beats truth result applies to human vision as it actually evolved is genuinely disputed, and it should be said plainly that it is disputed. But the disputed part is the strong claim. The weak claim is not in dispute at all, and the weak claim is enough for tonight. Your senses compress, discard, invent, delay, extrapolate, and construct, and they do all of it below the level where you can notice. Whatever is reaching you, it is a summary written by a system that was optimized for keeping you alive rather than for keeping you informed. Which is where this entry earns its place at number 10, at the shallow end, holding the door for everything below it. Every remaining reason on this list is going to be argued from evidence. Photographs of black holes, arrival times of gamma rays, interference patterns from molecules. Coincidence counts from detectors on two sides of a mountain. All of that evidence is real, and all of it is far more reliable than unaided human perception, because instruments were built precisely to get around the limits described above. But every one of those readouts, at the very last step, has to pass through a pair of eyes, and then through a nervous system that was tuned by natural selection for staying alive rather than for being right. There is no measurement anywhere in science that skips that step. The instruments extend the interface. They do not replace it. That is the shallowest thing this list will take away from you tonight, and it takes away only the messenger. The next entry takes away what the messenger was pointing at. Number 9. Solidity is a force law, not a substance. The chair holding you up is real. That is worth saying at the start of this entry, because the entry is going to take apart almost every intuition you have about what the chair is made of, and none of that is a claim that the chair is imaginary. What it is not what it seems. And the first measurement to say so was performed in a basement in Manchester using gold in 1909. Hans Geiger and Ernest Marsden were working under Ernest Rutherford, firing alpha particles at a sheet of gold foil so thin it was nearly transparent. The expectation was that the particles would pass through with slight deflections, because the atom was then pictured as a diffuse pudding of positive charge with electrons scattered through it. Most of them did pass through. But about 1 in 8,000 came back, deflected through more than 90 degrees, as though it had struck something small and immovable. Rutherford's own description of that result has never been improved on. He said it was as though you had fired a 15-inch naval shell at a sheet of tissue paper and it had come back and hit you. What the alpha particles had found was the nucleus. And the numbers that came out of that discovery are the reason this entry sits at number 9. A nucleus is about 1 femtometer across, which is 10 to the minus 15 meters. An atom is about 1/10 billionth of a meter across, 10 to the minus 10. The ratio between them is 100,000 to 1. If you scaled a nucleus up until it was a marble sitting on a table, 1 centimeter wide, then the atom around it would be a kilometer across, and the next marble would be a kilometer away. By volume, the arithmetic becomes harder to hold. The nucleus occupies something like 1 part in 1,000 million of the atom. Written as a percentage, an atom is about 99.99999999999% empty. There is a standard way of making that felt, and it holds up. If every atom in every human being alive was squeezed until the emptiness was gone, and the nuclear matter of all 8,000 million people were packed together at the density of a nucleus, the entire species would fit inside the volume of a sugar cube. That is the version of this fact that circulates, and it is correct as far as it goes. But it is also misleading, and the correction matters more than the fact. The atom is not empty. The word is wrong. An electron is not a small ball orbiting in a void, the way the diagrams show. It is a standing wave of probability, spread through the whole volume of the atom, with a shape determined by the equations that govern it. The atom is not a nucleus with a lot of nothing around it. It is a nucleus embedded in electron, all the way out to the edge. The space is not vacant. It is occupied by something that has no surface, which raises the question that this entry is really about. If nothing down there is solid, why does the floor hold? The answer is a rule written down by Wolfgang Pauli in 1925, and it is called the exclusion principle. No 2 electrons can occupy the same quantum state at the same time. Push 2 atoms together, and their electrons are forced into higher energy states, and that costs energy, and the cost rises steeply. What you experience as contact is that cost being paid. Add ordinary electromagnetic repulsion between the electron clouds, and you have the entire physics of touch. The floor is not stopping your foot because it is made of stuff, and your foot is made of stuff, and stuff cannot pass through stuff. The floor is stopping your foot because moving further would require rearranging quantum states, and that is expensive. Which means, stated in the plainest way it can be stated, you have never touched anything. Not once, not in your entire life. The sensation of contact is the electromagnetic field of the electrons in your fingertip pushing back against the electromagnetic field of the electrons in the object, across a gap that never closes. Every handshake, every held hand, every time you have ever picked something up, the gap was always there. Hold that sentence too. Like the number about the eye, it is going to return later on this list, and when it does, it will mean something almost exactly opposite to what it means here. This is not a poetic reading of the physics, incidentally. It was proved. Freeman Dyson and Andrew Leonard demonstrated in 1967 that the stability of ordinary matter follows from the exclusion principle, and Elliot Lieb and Walter Thirring produced a far simpler proof in 1975. The result is that without exclusion, matter would collapse in on itself, and the energy released in doing so would be enormous. Volume is not a property that stuff has. It is a property that quantum statistics enforce. Now to the mass, because the mass is stranger than the volume. A proton contains 3 valence quarks. It is natural to assume that the proton's mass is the sum of those quarks' masses, in the same way that a bag of sand weighs what the sand weighs. It is not. The 3 quarks account for roughly 1% of the proton's mass. The other 99% is the energy of the gluon field binding them, and the kinetic energy of the quarks moving inside, converted into mass by Einstein's relation, running in the direction it is rarely quoted in. So very nearly all of your body's mass is not substance. It is binding energy, held in a field, behaving as weight. This was not merely asserted by theorists. In 2008, Stefan Dürr and colleagues computed the masses of the light hadrons from first principles, using lattice quantum chromodynamics on a supercomputer, and published the results in the journal Science. Starting from the field theory alone, with no measured masses put in by hand, they reproduced the observed proton and neutron masses to within a few percent. The 99% that is not quarks came out of the calculation exactly where the measurements said it should be. The Higgs field, whose associated particle was announced by the ATLAS and CMS collaborations at CERN on the 4th of July 2012, at a mass near 125 giga-electronvolts, is what gives the fundamental quarks and the electron their rest mass. It is a genuine discovery, and it explains the 1%. It does not explain the 99%. The deeper description underneath all of this is quantum field theory, and it removes particles as objects altogether. In that framework, an electron is not a thing. It is a quantized excitation, a ripple, in an electron field that fills all of space. This is the cleanest available answer to a question that would otherwise be very strange. Why is every electron in the universe exactly identical to every other electron, to the limit of every measurement ever made? Because there are not many electrons. There is one field, and the electrons are the places where it is excited. Even the vacuum is not what the word suggests. Hendrik Casimir predicted in 1948 that 2 uncharged metal plates, placed a micrometer apart, would be pushed together, because the narrow gap between them excludes some of the field modes that exist outside it, leaving a pressure imbalance. Steve Lamoureux measured that force in 1997 and found agreement with the prediction at the level of a few percent. 2 neutral objects, in empty space, pushed together by the emptiness. The same emptiness shows up inside the atom. In 1947, Willis Lamb and Robert Rutherford measured a small displacement in the energy levels of hydrogen that no existing theory predicted. The displacement is caused by the electron interacting with vacuum fluctuations. Quantum electrodynamics was built to account for it, and it does. And this is the point at which the whole picture stops being a story and becomes the most precisely verified thing in the history of science. The magnetic moment of the electron has been calculated from quantum field theory and measured in the laboratory, and the two agree to roughly 1 part in a million. There is no other comparison between prediction and measurement anywhere in science that is this good. The theory that achieves it says that the electron is an excitation of a field with no measured size at all. Experiments bound its radius to below 10 to the minus 18 meters, which is at least 1,000 times smaller than a proton, and there is no evidence it has any size whatsoever. There is a place in the universe where the emptiness actually is removed, and it is worth visiting for a moment, because it turns the sugar cube arithmetic into an object. When a massive star collapses and its core is compressed past the point where electron exclusion can hold it, Protons and electrons are forced together into neutrons, and what remains is a neutron star, a sphere roughly 20 kilometers across, with more mass in it than the Sun. A single teaspoon of that material has a mass of about 1,000 million tons. That is what an atom looks like with the space taken out, and it takes the gravity of a dying star to do it. The rule that keeps quarks inside the proton is stranger still, and it runs backwards from every other force you have experience of. Gravity and electromagnetism weaken with distance. The strong force does not. Pull two quarks apart, and the energy stored between them rises without limit, until there is enough of it to create a new pair of quarks out of the vacuum, and instead of two separated quarks, you have two new particles. No quark has ever been observed alone. At very short range, on the other hand, the force nearly vanishes, and the quarks rattle around almost freely. That behavior is called asymptotic freedom, and David Gross, David Politzer, and Frank Wilczek received the Nobel Prize in 2004 for working out why it happens. The force that holds the nucleus together is not even that force directly. It is a residue of it, a leakage of the color force between quarks that spills slightly outside each proton and neutron and binds them to their neighbors, in almost exactly the way that chemical bonding is a leakage of electromagnetism outside the atom. The nucleus is held together by a side effect. Even the constants are not constant. The fine structure constant, which sets the strength of the electromagnetic interaction, is usually quoted as 1/137. That is its value at low energies. Measured at the mass of the Z boson, it climbs to about 1/128, because the vacuum around a charge is filled with virtual pairs that partly screen it, and the closer you get, the less screening there is. The strength of electromagnetism depends on how hard you look. And then there is the number that sits underneath this entire entry like a crack in the floor. If you take quantum field theory and ask it what the energy density of empty space should be, and then compare that answer to the value actually measured from the expansion of the universe, the two disagree by something like 120 orders of magnitude. That is a 1, followed by 120 zeros. It is the largest disagreement between a prediction and a measurement in the history of the subject. It has been known about for decades, and nobody has resolved it. The physics that describes matter to 12 decimal places cannot tell you what nothing weighs. John Wheeler had a name for what he expected space-time to look like at the smallest scales, where all of this would have to be sorted out. He called it quantum foam in 1955, and the name has stuck for 70 years without anyone managing to photograph it. One last thing about the atoms themselves, which is easy to say and hard to absorb. About 90% of the atoms in your body, counted individually, are hydrogen, and almost every one of those hydrogen nuclei was assembled in the first few minutes after the Big Bang and has not been altered since. The heavier atoms, the carbon and the oxygen and the iron, were built inside stars and scattered when those stars died. The field excitations currently arranged into a person have been in that arrangement for a few decades and in existence for 13,800 million years. So the account of matter that survives all of this is unfamiliar but not mysterious. There are fields. They fill space. Their excitations are what we call particles. Those excitations bind together, and the energy of the binding is what registers on a scale as weight. The volume they occupy is enforced by a rule about quantum states rather than by anything having a surface. And solidity, the thing you can feel with your hand right now against whatever you are holding, is a force law with a very steep curve. None of that makes the chair less real. It makes the chair less like a chair. What matters for this list is where it leaves us. Number 10 took away the reliability of the observer. Number 9 has taken away the solidity of the thing being observed. Between them, the world has gone from a set of solid objects seen accurately to a set of field excitations reported by a compressed and heavily edited interface. But both entries so far have left the stage alone. The room, the sequence of moments in it, the fact that there is a now and that it is moving, all of that has been sitting quietly underneath both entries, unexamined. The next reason on this list takes away something we do not usually think of as a thing at all. Number 8. Time does not flow. This one takes away the passage of time. Not time itself, which stays exactly where it is, but the moving present, the sense that this moment is happening and the last one is gone. If the physics is read the way most physicists read it, that motion is not a feature of the universe. It is a feature of you. The argument begins in 1905, with a paper that is usually remembered for something else. Albert Einstein's special relativity is remembered for the speed of light and for the equation about mass and energy. Its most consequential result for tonight is quieter and is called the relativity of simultaneity. Two events that happen at the same moment according to one observer do not happen at the same moment according to another observer moving relative to the first. There is no universal now. There is no master clock. Each state of motion carries its own answer to the question of what is happening right now elsewhere, and all of those answers are equally correct. Hermann Minkowski, who had been Einstein's mathematics teacher and had thought little of him as a student, saw the geometric meaning of this within 3 years. In a lecture in Cologne in 1908, he said that space by itself and time by itself were doomed to fade away into mere shadows, and that only a union of the two would preserve an independent reality. He was not speaking loosely. He meant that the correct object is a four-dimensional structure, and that carving it into space and time is something observers do, not something the universe does. The consequence of that is easier to feel with a specific example, and the standard one involves the galaxy next door. Picture an ordinary pavement on an ordinary evening. Two people are about to pass each other, walking in opposite directions at a comfortable speed, perhaps 5 kilometers an hour. They are perhaps a meter apart. Nothing about the scene is unusual. One of them is thinking about dinner. Now hold the moment they draw level and ask what is happening right now in the Andromeda galaxy, 2.5 million light-years away. Each walker has an answer, because each walker's frame of reference defines a plane of simultaneity, a slice through the four-dimensional structure that says which distant events count as now. The two walkers are moving relative to each other by a few kilometers an hour, which tilts their slices relative to each other by a fraction of a degree so small it has no name. But a slice extended across 2.5 million light-years amplifies that tilt enormously. By the time the two planes reach Andromeda, they are separated by days. So the walker heading east has an Andromeda in which a particular event has already happened. The walker heading west has an Andromeda in which that event is still in the future. They are standing beside each other. They can shake hands. Their nows differ by days, 2.5 million light-years away, and both of them are right. That argument was developed by C. W. Reitdiek in 1966, and independently by Hilary Putnam in 1967, and Roger Penrose gave it the wide audience it has now in The Emperor's New Mind in 1989. The arithmetic is not exotic. The offset grows as distance multiplied by relative velocity, divided by the square of the speed of light, and at 2.5 million light-years, walking pace is more than enough. What the argument establishes is uncomfortable in a specific way. If the walker heading east has a now in which an Andromedan event has occurred, then that event is real. If the walker heading west has a now in which it has not occurred, then it is not yet real. Both cannot be true of a universe in which reality is defined by a present moment. So either the present moment does not define what is real, or there is a preferred frame that physics has spent 120 years failing to find. Most physicists take the first option. The name for it is the block universe, and it says that past, present, and future all exist in the same sense as regions of a four-dimensional structure. Nothing happens to that structure. It simply is. The sense of moving through it is something that happens inside it, to systems that keep records, which is to say to us. The most famous statement of this idea was not made in a paper. It was made in a letter. In March of 1955, Einstein learned that Michele Besso had died. Besso had been his closest friend since they met as young men in Zurich, the person he argued physics with for more than 50 years, the one he had thanked in the 1905 paper. He was 76 years old, and he sat down to write to Besso's widow and son. What he wrote to them is that Besso had departed this strange world a little ahead of him, and that this meant nothing, because for those of them who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. He was not being clever. He was not consoling them with a metaphor. He was offering the family of his dead friend the one thing he had spent his life building, applied to the only problem it could not solve. Michele Besso still exists, in 1920 and in 1890, and in every other place on his own world line, and the fact that Einstein could no longer reach any of those places was a fact about Einstein's position, not about Besso. Einstein died 4 weeks later. Now, is any of this actually in the equations, or is it an interpretation laid over them? The answer is that it is in the equations by omission, and the omission is total. Newton's laws, Maxwell's equations, general relativity, the Schrödinger equation, every one of them works equally well, run forwards or backwards, and not one of them contains a term that marks which moment is the present. Physics has variables for position, momentum, field strength, and time coordinate. It has no variable for now. If the present moment were a feature of the world, 3 centuries of physics would have needed a symbol for it, and no symbol was ever needed. The direction we feel is real, but it comes from somewhere else. It comes from entropy. Ludwig Boltzmann's relation, connecting entropy to the logarithm of the number of microscopic arrangements consistent with what you can see, is engraved on his headstone in Vienna. It explains why an egg does not unbreak. There are overwhelmingly more arrangements that look broken than arrangements that look whole. But the explanation only works if the universe started in an extraordinarily ordered state, and that starting condition is not explained by anything. Roger Penrose estimated the improbability of the initial state at 1 part in 10 to the power of 10 to the power of 123, a number that cannot be written out because the exponent of its exponent is already larger than the number of particles in the observable universe. So the arrow you feel is not the arrow of time. It is the arrow of entropy, running away from a beginning that nobody can account for. And when physicists try to combine general relativity with quantum mechanics, the situation becomes more pointed still. The Wheeler-DeWitt equation, written down by Bryce DeWitt and John Wheeler in 1967, is what you get when you quantize general relativity in the standard way. Its central statement is that the Hamiltonian, the operator that generates change in time, acting on the wave function of the universe, gives 0. The wave function of the universe does not evolve. There is no time parameter for it to evolve in. This is known in the field as the problem of time, and it has been open for 58 years. If that is what the universe as a whole looks like, the obvious question is why anything inside it appears to change. Don Page and William Wouters proposed an answer in Physical Review D in 1983, and it is elegant enough to state in one sentence: divide the universe into a clock and everything else, and entangle the two. The combined state is static. But an observer who is part of everything else, and who is correlated with the clock, will find that the rest of the universe changes as a function of the clock reading. Time is not something the universe does. It is a correlation between parts of it. For 31 years, that was a mathematical curiosity. Then, it was demonstrated in a laboratory. Ekaterina Moreva, Giorgio Brida, Marco Gramegna, Vittorio Giovanetti, Lorenzo Marcone, and Marco Genovese published an experimental illustration in Physical Review A in 2014. They entangled two photons in polarization. One photon was designated the clock. An observer who became correlated with the clock photon, by measuring it, found that the second photon evolved exactly as the mechanism predicts. An external observer, measuring only global properties of the pair without touching the clock, could demonstrate that nothing about the pair was changing at all. The same physical system, at the same moment, was both static and dynamic. Which one it was depended entirely on where the observer stood relative to it. None of this is a reason to think time is unreal in the practical sense, and it is worth pausing on how thoroughly the effects are measured, because the block universe is not a philosophy. It is engineering. The atomic clocks aboard the GPS satellites run about 38 microseconds per day faster than clocks on the ground. That figure is the sum of two effects pulling in opposite directions, a gain of about 45 microseconds because the satellites sit higher in the Earth's gravitational field, and a loss of about 7 because they are moving at nearly 14,000 kilometers an hour. If the correction were switched off, positions would drift by roughly 10 kilometers a day, and satellite navigation would be useless within about 2 minutes. The effect has also been measured at the scale of a room. In 2010, Chin-Wen Cho, David Hume, Till Rosenband and David Wineland at the National Institute of Standards and Technology in Colorado used a pair of optical clocks to resolve gravitational time dilation across a height difference of 33 centimeters. Raise a clock by about the height of a stack of books, and it runs measurably faster. They also resolved the effect of motion at about 10 meters per second, which is the speed of a fast jog. Joseph Hafele and Richard Keating did the crude version first, in 1971, by buying seats on commercial airliners for 4 cesium clocks and flying them around the world eastward and then westward. The clocks came back disagreeing with the ground, in both directions, by tens to hundreds of nanoseconds, and the disagreement matched the prediction. The twin situation that people find paradoxical is not a paradox at all once the geometry is clear. Proper time is the length of a path through space-time. Two travelers who leave the same event and meet again at a later event have taken different paths, and different paths have different lengths, in exactly the way that two roads between the same pair of towns have different distances. Nobody finds it strange that one road is longer. Time works the same way, and the odometer is a wristwatch. There are stranger corners of this than the ones already covered, and 2 of them are worth walking into briefly. The first is a birthday present. In 1949, Kurt Gödel, who had already dismantled the foundations of mathematics and who lived a few doors from Einstein at Princeton, found an exact solution to Einstein's field equations describing a universe that rotates. In that universe, closed time-like curves exist, paths through space-time that return to their own starting event. A traveler following one would arrive at their own past, not by exceeding the speed of light, but by following the local geometry the whole way. Gödel presented the solution to Einstein as a gift for his 70th birthday. Our universe does not appear to rotate in the way the solution requires, so it is not a description of where we live. But it is a legitimate solution to the equations, which means that general relativity does not, on its own, forbid the past from being a place you can reach. The second is a picture in which time is removed altogether rather than frozen. Julian Barbour has argued for decades that the fundamental description contains no time and no history, only an unordered space of possible configurations of the universe, which he calls Platonia. Every instant is a point in that space. Some of those instants contain records that appear to describe other instants, and the appearance of a past is nothing more than the presence of those records in the present configuration. On that reading, there is no flow to explain, because there is nothing to flow through. There is also a symmetry result that is easy to state and difficult to shake off. The CPT theorem holds that the laws of physics are invariant under the combined operation of reversing charge, mirroring space and running time backwards. It is one of the most solidly established results in field theory. Its meaning for tonight is that the laws themselves, taken as a whole, cannot tell forwards from backwards. Something outside the laws has to supply the difference, and the only candidate anyone has is the entropy of the initial state. There is exactly one operation in standard physics that does not run cleanly in both directions, and it is measurement. A quantum system evolves smoothly and reversibly right up until it is measured, and then the outcome is one thing rather than a superposition of things, and that step cannot be undone. This is the reason the problem of the arrow of time and the problem of measurement keep turning out, on close inspection, to be the same argument approached from two sides. It is also the reason the next several entries on this list are going to keep circling the same question from different directions. A final piece of geometry, because it turns an abstraction into something a person could, in principle, experience. An observer under constant acceleration develops a horizon behind them. Events beyond it can never send light that catches up, so from the accelerating observer's point of view, those events will never happen, no matter how long they wait. It is called a Rindler horizon, and it is produced by motion alone, with no black hole and no cosmology involved. Accelerate hard enough for long enough, and part of the universe simply stops being able to reach you. The past you are leaving does not merely recede. It becomes unreachable in principle. And there is a version of Ravelli's position worth stating precisely, because it is the most moderate of the three views on offer. His thermal time hypothesis proposes that the flow of time is not fundamental and not illusory either, but statistical. It emerges from the particular coarse-grained state a system happens to be in the same way that temperature emerges from molecular motion. On that reading, time flows for you because of what you are, not because of what the universe is. Which is a smaller claim than Barbour's, and a larger one than most people are comfortable with. Now, the honest position. Eternalism is widely held among physicists, but it is not unanimous, and it is not proved. Lee Smolin argued in Time Reborn in 2013 that the passage of time is real and fundamental, and that the block is an artifact of the mathematical convenience of treating time as a coordinate. Tim Maudlin has argued along similar lines from the philosophy of physics. Carlo Rovelli, in The Order of Time in 2018, takes a third position, that time is real, but thermodynamic and perspectival, arising from the coarse-grained state of a system rather than from the geometry underneath. These are serious people making serious arguments, and the question is open. But if the block picture is right, one consequence follows that is worth sitting with for a moment before this entry ends. Nothing that has happened is gone. Every conversation, every ordinary afternoon, every person who has died is a region of a four-dimensional structure that exists. The reason none of it is accessible is not that it has been destroyed. It is that you are somewhere else on your own world line, and the direction that would take you back is not a direction you can walk in. Time became, in this entry, the first thing on the list to stop being a flow and start being a shape. The next entry asks whether the shape is smooth. Number 7. Space may be pixelated, and every search so far has come back clean. This entry takes away smoothness. Not the contents of space, and not its dimensions, but the assumption that space is continuous, that between any 2 points there is always another point, and that you could keep halving a distance forever if you had the patience. It is also the one entry on tonight's list where the searching has actually been done at considerable expense and has come back empty. That makes it unusual, and it makes it honest, and it is the reason it sits here at number 7 rather than higher. The scale in question has a name and a number. It is called the Planck length, and it is 1.616 times 10 to the minus 35 meters. The way that number was arrived at is worth a moment because it is one of the odder pieces of physics history. Max Planck derived it in 1899. Quantum mechanics did not exist. Relativity did not exist. Planck simply noticed that if you take the gravitational constant, the speed of light and the quantum of action he had just introduced, there is exactly one way to combine them that produces a length, and exactly one way that produces a time. The length came out at 10 to the minus 35 meters. The time, which is how long light takes to cross that length, came out at 5.39 times 10 to the minus 44 seconds. He had no theory that said anything happens at those values. He had arithmetic and a suspicion. Making the length felt requires a comparison, because the number is meaningless on its own. A proton is about 10 to the minus 15 meters across, which already sits far below anything a person can picture. A proton is 100 million Planck lengths wide. Scale the Planck length up until it is 1 millimeter, about the thickness of a fingernail, and on that same scale, a single proton would be roughly 100 light-years across. The gap between the smallest thing we routinely talk about and the smallest thing physics can define is larger than the gap between a person and a galaxy. There is a reason physicists expect the description of space to change down there, and it is not a hunch. To probe a small distance, you need a short wavelength, and a short wavelength means high energy, and energy gravitates. As you push the wavelength toward the Planck length, the energy you have concentrated in that small region becomes enough to form a black hole. The measurement destroys the thing being measured, and worse, it hides it behind a horizon. This is not a limit of instruments. It is a limit built into the relationship between quantum mechanics and gravity, and it is the reason the Planck scale is treated as a genuine flaw rather than merely a very small number. How far are we from it? The Large Hadron Collider, the largest machine ever built, resolves structure down to about 10 to the minus 19 meters. That is 16 orders of magnitude short. To reach Planck energy with accelerator technology of the kind we know how to build, you would need a ring roughly the size of the galaxy. This is not a funding problem. So why take discreteness seriously at all? Because of a result that came out of black hole physics and refused to go away. Jacob Bekenstein in 1972 and Stephen Hawking in 1974 established that a black hole carries entropy, and that the entropy is 1/4 of the area of its event horizon, measured in units of the Planck area. Entropy counts states. It counts the number of distinct microscopic arrangements a system can be in. And when the count of a system's states comes out as an area divided by a fixed small area, the natural reading is that the surface is tiled. That the horizon is made of a very large number of very small units, each one a Planck area, each one carrying about a bit. For a black hole of 1 solar mass, the count comes out around 10 to the 77th. Hold on to the phrase Planck area pixel. It is going to appear twice more tonight, in 2 entries much further down this list, doing entirely different jobs each time. Once the idea is on the table, several serious frameworks take it as a starting point. Loop quantum gravity makes discreteness explicit and unavoidable. In that framework, area and volume are not continuous quantities but operators with discrete spectra, in the same way that the energy levels of an atom are discrete. There is a smallest possible non-zero area of order 10 to the minus 70 square meters, and no measurement can return a value between 0 and that. Space is not a container that can be subdivided indefinitely. It has a grain. Causal set theory takes a different route to the same place. Proposed by Raphael Sorkin in 1987, it replaces the continuum with a discrete collection of events and a single relation saying which came before which. Everything else, including the apparent smoothness of space-time, is supposed to emerge from the counting. Its most notable moment came before the observation it anticipated. The framework suggested that the vacuum energy should fluctuate around a small, non-zero value of roughly the size that turned out to be measured, and it suggested it in 1987, 11 years before the supernova surveys of 1998 found the expansion of the universe accelerating. That is not proof, and Sorkin's estimate was rough. But it is a prediction made before the data, which is rare enough in this area to be worth stating. Then there is the frankly computational picture, and 2 names carry it. Gerard Hooft shared the Nobel Prize in 1999 for work on the Standard Model, which is to say, he is not a marginal figure. Since the 1990s, he has argued for what he calls a cellular automaton interpretation of quantum mechanics, in which a deterministic automaton operating at the Planck scale underlies quantum behavior, and the probabilities we observe come from our inability to track its states. He gave the idea a book-length treatment in 2014. Stephen Wolfram launched a physics project in 2020, modeling space as an evolving hypergraph, a network of nodes and connections that updates by simple rules. With an elementary length he estimates near 10 to the minus 93 meters. Both programs are honest about being programs. Neither has produced a derived, tested prediction that distinguishes it from ordinary physics, and this entry does not pretend otherwise. What makes number 7 worth 3 hours of anyone's attention is that the idea has been tested 3 times by 3 completely different methods. The first test used a gamma-ray burst. If space were a simple lattice, light of different energies would travel at very slightly different speeds because the shortest wavelengths would begin to notice the grain. Over an ordinary distance, the difference would be undetectable. Over a cosmological distance, it would accumulate into a measurable delay. On the 10th of May 2009, the Fermi Gamma-Ray Space Telescope detected a short gamma-ray burst catalogued as GRB 090510 from a source roughly 7,300 million light-years away. The burst lasted a fraction of a second. Among its photons was one carrying 31 giga-electron volts, which arrived 0.829 seconds after the trigger. That single photon did most of the work. Its energy is high, the distance it traveled is enormous, and the burst it came from was short enough to give a sharp reference point. The analysis, published in Nature later that year, excluded a linear energy dependence of the speed of light all the way past the Planck scale, to better than the Planck length divided by 1.2. Whatever space is made of, it is not made of a simple grid of that kind. A follow-up analysis by Vasileo and colleagues in Nature Physics in 2015 used the same class of observation to set a Planck scale limit on random space-time fuzziness as well. The second test was an accident. The GEO 600 gravitational wave detector near Hanover in Germany showed unexplained noise in the 300 to 700 Hz band that its builders could not account for. In 2008, Craig Hogan of Fermilab suggested it might be holographic noise, a Planck-scale jitter in the position of the beam splitter, an intrinsic uncertainty in where anything is. The suggestion drew a great deal of attention. The collaboration eventually traced the excess to conventional sources, and the noise stopped being interesting. But Hogan took the idea seriously enough to build an instrument specifically to look for it, and the third test is the result. The Fermilab holometer ran from 2014 to 2015. It consisted of two co-located Michelson interferometers, each with 40-meter arms and power recycling, positioned so that a genuine space-time signal would appear in both at once, while ordinary local noise would not. The cross-correlation between them was the measurement. The sensitivity reached the level of about 10 to the minus 18 meters of position correlation across 40 meters of arm, which is 1,000 times smaller than a proton. After a year of data, the result was clean. No holographic noise at the predicted level. The exclusion was published, and the specific model Hogan had proposed was ruled out. Hogan's own summary of his own null result is the reason this entry belongs on the list rather than in a footnote. What mattered, he said, was that a technique now exists for measuring space-time at this level, even though the signal did not appear. That is what a good negative result looks like. LIGO, measuring displacements at the level of 10 to the minus 19 meters in order to detect gravitational waves, has likewise seen nothing that looks like Planck-scale jitter. Before leaving the searches behind, there is a set of numbers that sits underneath this entire entry and explains why so many physicists find the pixel idea attractive, even without a detection. It concerns the cost of information. In 1961, Rolf Landauer, working at IBM, proved that erasing a single bit of information has an unavoidable energy cost. Not the cost of running the machinery, which can in principle be made arbitrarily small, but a floor set by thermodynamics itself. Erasing one bit at a given temperature must release a specific minimum quantity of heat. For a long time, this was regarded as a theoretical statement about idealized computers. In 2012, Antoine Beroux and colleagues published a direct measurement of it in Nature, using a single microscopic bead held in an optical trap as a 1-bit memory, and found the predicted flaw exactly where Landauer had put it. The implication is not a small one. Information is not an abstraction that floats above physics. It has a price, denominated in energy, enforced by the same thermodynamics that governs steam engines. And once information has a price, it becomes reasonable to ask how much of it a given volume of the universe can hold, which is the question the Planck area pixel is an answer to. Seth Lloyd worked out the ceiling in 2000, in a paper on the ultimate physical limits to computation published in Nature. A kilogram of matter, arranged in the most efficient possible way, can perform about 10 to the 51st operations per second and store about 10 to the 31st bits. Those limits do not come from engineering. They come from the speed of light, from the quantum of action, and from the fact that packing too much energy into too small a space produces a black hole. A laptop that reached them would, at the moment of switching on, be a small fireball. Applied to everything, the same reasoning gives a figure that is difficult to look at directly. Estimates of the total entropy of the observable universe put it near 10 to the 104th units, and the overwhelming majority of that is not in the stars or the gas or the galaxies. It is in the horizons of supermassive black holes. Everything visible, every star and planet and living thing, contributes a rounding error against the information content of the objects nothing ever comes back out of. There is one more probe of Planck-scale structure worth naming, because it uses a different messenger. The Ice Cube Observatory at the South Pole, a cubic kilometer of Antarctic ice, instrumented with more than 5,000 light detectors, watches for neutrinos from astrophysical sources. Neutrinos interact so weakly that they arrive undisturbed from places light cannot leave, and their travel times across cosmological distances have been used to set independent limits on whether the vacuum treats different energies differently. Those limits, too, are consistent with a perfectly smooth vacuum. It is worth being precise about what a lattice would actually give away, because the tests all exploit the same weakness. A cubic grid has axes. It has directions along which it looks different from the directions in between, in the way that a chessboard looks different along a rank than along a diagonal. Perfect rotational symmetry is the one thing a grid cannot have. Every experimental attack on discreteness in the last 20 years has been a search for that broken symmetry, whether in the arrival times of photons, the correlated jitter of mirrors, or, as we will see at the very end of tonight's list, the arrival directions of the highest energy particles in the universe. And a small piece of context that makes the Planck scale less alien than the numbers suggest. The Planck length is unimaginably small, and the Planck energy is unimaginably large, but the Planck mass, which is the same quantity expressed a third way, comes out at about 22 micrograms. That is roughly the mass of a flea's egg, or a grain of very fine sand. It sits comfortably within human experience. The Planck scale is only extreme when you express it as a length, or as an energy density. Expressed as a weight, you could hold it, if you could find it. What separates Hogan's proposal from the rest of this material is worth stating clearly, because it is the property that made it worth building a machine for. His holographic noise had a specific predicted amplitude at a specific frequency. It could be excluded, and it was. Loop quantum gravity's minimum area, the causal set structure, and the various computational pictures do not currently make predictions of that kind, which is precisely why no instrument has been built to rule them out. So the honest position on number 7 is this. There are strong theoretical reasons to think space has a smallest scale, coming from black hole entropy, from loop quantum gravity, and from causal sets. There are frameworks that build the whole of physics on it. And there is not one positive detection. 3 independent searchers have looked at 3 different scales, using photons from across the universe and mirrors in an Illinois field, and all 3 came back with a clean image. That does not falsify the idea. The pixels may simply be far smaller than any model that predicted a visible signature. Absence of evidence at 10 to the minus 35 meters is not much of anything. But it does mean this entry cannot claim what the entries below it can claim. Nothing was found here. The next entry is the opposite case. The searching was done, the experiment was run, and something was found. Number 6. There may be no such thing as an observer-independent fact. This one takes away shared facts. Not truth in general, and not the existence of the world, but a much more specific assumption that almost nobody examines, that when something happens, it happens for everybody. That there is one event, one outcome, and that any observer who checks will find the same answer, because the answer is a property of the world rather than a property of the person asking. Between 2018 and 2020, that assumption was turned into a mathematical statement, shown to be incompatible with quantum mechanics plus two very ordinary-sounding conditions, and then tested in a laboratory. That sequence is why this entry outranks the three below it. The previous entries described things about the world that were surprising. This one describes something about the world that appears not to be well defined. It begins as a thought experiment, and it is 65 years old. In 1961, Eugene Wigner, who had received the Nobel Prize for his work on symmetry in physics, published an essay on the relationship between mind and body that contained a short scenario. It has been called Wigner's friend ever since. The setup is minimal. A friend is inside a sealed laboratory, completely isolated from the outside. Inside, the friend performs a measurement on a quantum system, something as simple as measuring the polarization of a photon. The friend sees a definite result. From the friend's point of view, an event has occurred, an outcome has happened, and it is now a fact. Wigner is outside, and he has had no interaction with the laboratory whatsoever. According to the rules of quantum mechanics, applied consistently, Wigner must describe the entire contents of that laboratory, the photon, the apparatus, and the friend, as a single system in a superposition. Not a system whose value he happens not to know. A system that is genuinely in a combination of the state in which the friend saw one outcome and the state in which the friend saw the other. So there are two descriptions of one situation, both derived correctly from the same theory by competent physicists, and they disagree about whether anything happened. For a very long time, this was regarded as a curiosity, the kind of thing raised over dinner at conferences and then set down again, because there was nothing to be done with it. It concerned an isolated laboratory that could not be built, and a friend who could not be unmeasured. Then it stopped being a curiosity, because someone turned it into a theorem. In 2018, Daniela Frauchiger and Renato Renner published a paper in Nature Communications with a title that is unusually blunt for a physics journal. Quantum theory cannot consistently describe the use of itself. Their construction extends Wigner's scenario to 4 agents. 2 of them are sealed observers, each in their own isolated laboratory, each performing measurements. 2 more are outside, measuring the sealed laboratories as wholes. Crucially, each agent is allowed to reason about what the other agents have concluded, using standard quantum mechanics, in exactly the way a physicist would. The result is that in a small fraction of runs, the agents reach conclusions that are not merely different, but flatly contradictory. One agent concludes, with certainty, that another agent has predicted the opposite outcome with certainty. Both chains of reasoning are correct applications of the textbook rules. They cannot both be right. The escape routes exist, and every one of them is expensive. Either quantum mechanics does not apply to observers, which means there is a size at which the theory stops working and nobody knows where. Or measurements do not have single outcomes, which is a much larger claim than it sounds. Or agents cannot reason about other agents' conclusions in the way the argument assumes, which would place a limit on rational inference itself. Czeslaw Bruckner sharpened this into a general no-go statement about observer-independent facts, that quantum theory, together with a small set of assumptions almost anyone would accept without noticing, cannot support the idea that measurement outcomes are facts for everyone. At which point the question became experimental. On the 20th of September 2019, Massimiliano Proietti, Alexander Pixton, Francesco Graffiti, Peter Barrow, Dimitro Kundis, Cyril Branciard, Martin Ringbauer, and Alessandro Fedrizzi published a paper in Science Advances titled Experimental Test of Local Observer Independence. It came out of Heriot-Watt University in Edinburgh, with collaborators in Grenoble and Innsbruck. They built an extended Wigner's friend scenario using 6 photons and 4 observers. 2 of the photons played the role of friends, each making a measurement inside its own effectively sealed context. 2 further measurement stations played the role of Wigner's, measuring those contexts as wholes. The whole arrangement was designed so that a specific Bell-type inequality would hold if the friends' outcomes were absolute facts, true for everyone. The inequality was violated by 5 standard deviations. The team's own framing of the result is careful, and it deserves to be quoted in the spirit in which it was written, rather than the spirit in which it was reported. If one holds on to locality and to the freedom of experimenters to choose what they measure, then the result means quantum theory has to be interpreted in an observer-dependent way. Not that reality is subjective, that the theory, applied consistently, does not deliver a single set of outcomes shared by all observers. 14 months later, a group at Griffith University in Australia made the argument stronger, and the way they made it stronger is the reason this entry sits at number 6 rather than lower. Kokwei Bong, Anibal Utreras Alarcon, Farzad Ghaffari, Yongcheng Liang, Nora Tischler, Eric Cavalcanti, Jeff Pride and Howard Wiseman published a strong no-go theorem on the Wigner's friend paradox in Nature Physics in December 2020. Their assumption set has a name that sounds almost cheerful. They call it local friendliness. It has 2 parts, and both are worth stating in plain language because their plainness is the point. The first is called absoluteness of observed events. It says that an event observed by any observer is an absolute event. If it happened, full stop, not merely relative to somebody. The second is called local agency. It says that a free choice made here cannot influence events outside its future light cone. Nothing you decide can affect anything that light from your decision cannot reach. That is the entire assumption set. And here is the important part. Local friendliness does not assume determinism, and it does not assume that particles carry pre-existing values. Bell's famous argument, which we will come to at number 5, does assume those things. Because local friendliness assumes strictly less, violating it rules out strictly more. Their photonic experiment violated the local friendliness inequalities. Now the limitation, stated plainly, because this entry would be dishonest without it. In both experiments, the friends were single photons standing in for observers. Nobody has sealed a human being inside a laboratory, had them make a measurement, and then reversed the process. Nobody can, and the reason is worth understanding, because it is not merely a matter of engineering budgets. The protocol requires that the friend's measurement be undone. Not forgotten. Undone, reversed at the level of every particle involved, including every particle of the friend, in a way that restores the exact earlier state. For a photon that is difficult. For a nervous system that has formed a memory, it means erasing the memory and every physical trace of it, everywhere, and putting the system back the way it was. So the experiments do not prove that 2 people can disagree about what happened. What they establish is narrower and, in a certain way, harder to argue with. The theorems are assumption-level results. They say which combinations of assumptions cannot all be true at once, and they do not care what the friend is made of. The experiments confirm that quantum mechanics behaves exactly as the theorems require it to. If a human observer would behave differently from a photon, that difference is not in any theory anyone has written down. Something has to give, and the surviving options are all strange in their own way. It is worth walking through them, because each one is a different answer to the question of what a fact is. Objective collapse theories say that quantum mechanics is not the whole story, and that superpositions of large systems genuinely and spontaneously collapse into single outcomes. The best-known version was proposed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in 1986. On this view, there is a real physical process that turns possibilities into events, and facts are absolute after all. The cost is that quantum mechanics has to be modified and a new law of nature added. Many worlds, proposed by Hugh Everett in 1957 while he was a graduate student, says that all outcomes occur and that the appearance of a single result is an appearance from inside one branch. On this view, there is no contradiction between Wigner and his friend, because both descriptions are correct about different parts of a larger structure. The cost is the structure. Cubism, developed by Christopher Fuchs, David Mermin, and Rudiger Schack, says the whole problem comes from a misreading. A quantum state is not a description of a system, it is a description of an agent's expectations. Outcomes are personal experiences of agents, and were never meant to be objective events at all. The cost is giving up the idea that the theory describes the world rather than describing what to expect from it. Relational quantum mechanics, proposed by Carlo Rovelli in 1996, says that states are relations between systems rather than properties of systems, and that there is simply no view from nowhere. An outcome is always an outcome relative to something. The cost is that the phrase "what actually happened" stops having an unqualified meaning. The interesting development is that at least one of these is now being tested rather than debated, and it is losing ground. Objective collapse models make a prediction that other interpretations do not. If wave functions are being physically jostled into definite states by a real process, charged particles should occasionally radiate as a result, producing a faint and very specific glow. Experiments have gone looking for it in the deepest quiet available, the Gran Sasso National Laboratory in Italy, buried beneath 1,400 meters of rock to shield it from cosmic rays, using germanium detectors cooled and screened against everything else. In 2021, Sandro Donardi and colleagues reported in Nature Physics that the expected radiation is not there at the required level, and that the parameter-free version of the gravitational collapse model proposed by Lajos Diosi and Roger Penrose is excluded by the data. Collapse models are now squeezed from both directions, too weak, and they fail to produce outcomes at all, too strong, and they emit light that nobody can find. Meanwhile, the other end of the question is being pushed as well. How large can a system be and still be demonstrably in two states at once? Markus Arndt's group in Vienna has been raising that ceiling for 25 years, starting with 60-atom carbon molecules in 1999. In 2019, they published in Nature Physics interference from molecules of about 25,000 atomic mass units, containing around 2,000 atoms, sent through an interferometer 2 meters long and recovered as fringes on the far side. That is the record. It is also, and this is the number that keeps the whole field honest, about 20 orders of magnitude short of a bacterium. The gap between the largest thing demonstrably in superposition and the smallest thing anyone would call an observer is enormous, and every claim in this entry sits inside it. There are two pieces of history worth adding here, because they show that this entry did not arrive out of nowhere. The logical skeleton of the Frauschiger and Renner argument was built in 1992 by Lucien Hardy. His construction, usually called Hardy's paradox, describes a situation in which quantum mechanics assigns certainty to a set of statements that cannot all be true together, using nothing more than the ordinary rules and a particular entangled state. For 26 years, it sat in the literature as an oddity about particles. What Frauschiger and Renner did was put observers where the particles had been, and the oddity became a statement about reasoning. The second piece of history is a proposal that has been waiting for technology since 1985. David Deutsch pointed out that if you could build an artificial observer inside a quantum computer, you could ask it to record a measurement outcome, then reverse the entire computation and check whether the interference that survives is consistent with a single outcome having occurred. It is, in effect, Wigner's friend run on hardware, with a friend simple enough to be reversed. The photonic experiments of 2019 and 2020 are the closest anyone has come, and they are close in structure rather than in scale. Renner's own plain language summary of what his theorem shows is worth repeating exactly because it is so undramatic. There is no way, he has said, to make quantum theory tell one single story about what happened. Not a story we cannot access, or a story that is hard to compute. One story, of the kind every other physical theory provides without being asked. The reversibility requirement deserves one more sentence, because it is the hinge the whole subject turns on. The reason a sealed observer is such a strange object is that quantum mechanics, taken at face value, says the sealing is reversible. Everything inside the box, including whatever the friend now knows, is in principle recoverable, because unitary evolution destroys nothing. If that is true of a photon, and it demonstrably is, and if there is no size at which it stops being true, then it is true of a person. The measurement that felt like an event was, from outside, a rotation that could be rotated back. Nothing in any tested theory says otherwise. What stops it happening is difficulty, not law, and difficulty is not the kind of thing physics is usually willing to build a distinction on. It is also worth putting a number on how fast the ceiling is rising, because the pace decides whether this stays a thought experiment. The Vienna group's interference records have climbed by roughly 3 orders of magnitude per decade since the first buckyball experiments. 60 atoms in 1999. Around 430 atoms by 2011. Around 2,000 atoms and 25,000 atomic mass units by 2019. Extrapolating a curve like that is a hazardous business, and the difficulty rises faster than the mass does, because the molecule has to stay isolated from every stray photon and every thermal vibration for the whole flight. But the direction has not changed in a quarter of a century, and each step has been achieved by people who were told the previous step was the last one. And one comparison that makes the ranking on this list defensible. Bell's theorem, which is the subject of the next entry, assumes that measurement outcomes are determined by properties the particles already possess. That assumption is doing real work, and someone who rejects it can walk away from Bell's conclusion. Local friendliness assumes nothing of the kind. It assumes only that observed events are absolute and that free choices do not reach outside their own light cones. There is no hidden variable premise to reject. That is why the Griffith result is described as strictly stronger than Bell's, and why an entry about facts sits above an entry about properties on a list ranked by how much it removes. So the dispute at number 6 is not really about whether the moon is there when nobody looks. It is about whether the phrase, "what happened," names a property of the world or a property of a position inside it. That was a result about facts. The next entry is the older result underneath it, and it is the most thoroughly tested statement on tonight's list. Number 5. Local realism is not a philosophical worry. It was tested, and it lost. We are halfway down. It is worth taking 20 seconds to look back up the ladder before continuing, because the descent so far has been steeper than it feels. We began with a beetle on an Australian roadside, mating with a beer bottle, and the theorem that says his mistake is the normal condition of perception. We went from there to a flaw that holds because of a rule about quantum states, and a body whose mass is 99% binding energy. Then time stopped flowing and became a shape. Then the smoothness of that shape came into question, and 3 separate searches came back clean. And then the idea of a fact that is true for everybody turned out to be incompatible with quantum mechanics, plus 2 assumptions nobody would have thought to question. 5 entries. 5 things taken away. And every one of them still left standing the most basic assumption of all, which is that objects have properties. That is what number 5 removes, and unlike everything above it, this one is finished. There is no ongoing debate about whether it is true. There is a Nobel Prize awarded in 2022 for having established it. It starts with an objection, and the objection came from Einstein. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper asking whether the quantum mechanical description of physical reality could be considered complete. Their answer was no. Quantum mechanics predicts that 2 particles can be prepared so that measuring one immediately tells you something about the other, no matter how far apart they are. To Einstein, this was obviously not a signal traveling between them. It was obvious that the particles had left the source carrying prearranged answers, the way 2 people can leave a room with 1 glove each and know instantly what the other has. Quantum mechanics simply did not include those answers, which made it an incomplete statistical summary of a deeper theory. It is a good argument. It is careful. It is physically motivated, and for 29 years there was no way to decide it. It was a matter of taste. Some physicists agreed with Einstein and some did not, and there was no experiment anyone could imagine that would separate the 2 positions. Then a physicist in Geneva turned it into arithmetic. John Stuart Bell was an Irish physicist working at CERN on accelerator design. Foundations of quantum mechanics was not a respectable field in the 1960s. It was regarded as the sort of thing that had been settled by better men in the 1930s, and a young physicist who spent time on it was damaging his career. Bell worked on it anyway, on unpaid leave, in his own hours, and in 1964 he published a short paper titled On the Einstein-Podolsky-Rosen Paradox. What he proved is one of the most consequential results in the history of physics, and it can be stated without any mathematics at all. Suppose Einstein is right. Suppose each particle leaves the source, carrying a full set of instructions for what to do under every possible measurement, and suppose nothing travels between the 2 measurement stations faster than light. Bell showed that under those 2 assumptions alone, and regardless of what the instructions are or how they were generated, the correlations between the 2 sets of results must satisfy a specific inequality. There is a ceiling on how strongly correlated they can be. Quantum mechanics predicts a violation of that ceiling. So the 2 positions were no longer a matter of taste. They made different numerical predictions, and the difference could be measured. The version used in every experiment since was written down in 1969 by John Clauser, Michael Horn, Abner Shimoni, and Richard Holt. In their formulation, any theory of the kind Einstein wanted is bounded by the number 2. Quantum mechanics predicts a maximum of 2 times the square root of 2, which is about 2.828, a limit later shown to be fundamental by Boris Cyrelson. The gap between 2 and 2.828 is where the question lives. The first real test was run at Berkeley in 1972 by John Clauser and Stuart Friedman on almost no money, with equipment partly scavenged from around the laboratory. Clauser has said publicly, many times since, that he expected to find quantum mechanics wrong. He thought Einstein was right. He built the apparatus in order to demonstrate it. The inequality was violated. He had built the machine that proved his own position untenable, and he published the result. The next 20 years were a slow campaign to close the ways out. If the two detectors could communicate, the result proves nothing, because one station could adjust its behavior based on what the other was doing. So the settings had to be chosen after the particles were already in flight, and far enough apart that no signal at light speed could carry the news across. Alain Aspect, working at Orsay outside Paris between 1981 and 1982 with Philippe Grangier, Gérard Roget, and Jean Dalibard, built the apparatus that did it. Acousto-optic switches redirected each photon toward one of two differently oriented analyzers, and they switched every 10 nanoseconds while the photons were already traveling. The two stations were 12 meters apart, which light crosses in 40 nanoseconds. The choice was made after the photon had left, and it could not have reached the other station in time to matter. The inequality was violated again. Even that left gaps. Detectors were inefficient, so only a small fraction of pairs were ever registered, which meant assuming the detected sample was representative. And in principle, the settings, though switched rapidly, were not truly random. It took another 33 years to close everything at once. In 2015, Bas Henson and colleagues at Delft University of Technology published in Nature a loophole-free Bell test using electron spins in nitrogen vacancy centers in diamond, held in two laboratories 1.3 kilometers apart on opposite sides of the campus. The scheme was event-ready, meaning the experiment announced in advance which trials counted, which removes the sampling problem entirely, and the separation was large enough to close the locality loophole at the same time. Both loopholes in one experiment for the first time. Two photonic experiments from Vienna and from the National Institute of Standards and Technology confirmed it within months. That should have been the end of it. But there was one assumption left, and it is the strangest of them all. Bell's theorem assumes that experimenters are free to choose what they measure. If the settings were somehow correlated with the particles in advance, the whole argument collapses. So they went after that too, and the two attempts are among the more inventive things anyone has done with a physics budget. The first used people. The Big Bell test, published in Nature in 2018, recruited about 100,000 volunteers around the world who played a simple online video game whose only purpose was to generate unpredictable sequences of zeros and ones. 97 million bits came out of it, and those human choices were fed in real time to 12 laboratories on 5 continents to set their measurement bases. If the settings were pre-arranged, then so were the decisions of 100,000 people at their keyboards. The second used the sky, and it is the image to hold from this entry. Picture a volcanic ridge on the island of La Palma, in the Canaries, at night. The air is dry and very still, which is why the telescopes are here. 2 of them stand a few hundred meters apart, and neither is pointed at anything in this galaxy. One is locked onto a quasar roughly 4,000 million light-years away. The other is locked onto a different quasar, further still. Between them, an entangled pair of photons is created and sent in opposite directions. While that pair is in flight, a single photon from the first quasar arrives at the first telescope. It has been traveling since before the Earth existed, and it ends its journey by passing through a dichroic mirror that sorts it by color. Red or blue. That color, decided by the atomic physics of an object thousands of millions of years in the past, sets the angle of the analyzer that the entangled photon is about to meet. At the other station, a photon from the second quasar does the same thing. The settings for this experiment were not chosen by anyone. They were chosen before the solar system formed and delivered by light. Dominic Rauch and colleagues published the result in Physical Review Letters in 2018. The violation came out at 9.3 standard deviations, with a probability of about 7 times 10 to the minus 21 that it could have happened by chance. For a conspiracy of prearranged instructions to have faked that result, the correlation between the quasars and the detectors would have had to be arranged thousands of millions of years before either detector was built. In 2022, the Nobel Prize in Physics went to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. John Bell died in 1990 at the age of 62 of a cerebral hemorrhage. He had been nominated. He never received it. Clauser, who built his first apparatus hoping to prove that the world was ordinary, was 79 when the announcement came. Now, what is actually ruled out? Because this is the point where the popular version goes wrong. Reality is not ruled out. What is ruled out is a specific pair of assumptions taken together, and the pair has a name: local realism. Locality is the assumption that nothing influences anything outside its own light cone. Realism, in this technical sense, is the assumption that measurement outcomes are fixed by properties the particles already carried. At least one of those is false. The experiments do not tell you which. And it must be said clearly that this does not permit faster-than-light communication. Quantum mechanics is what physicists call non-signaling. Each measurement station, looking only at its own results, sees nothing but random noise. The correlation only appears when the two lists of outcomes are brought together and compared, and bringing them together requires an ordinary message traveling at or below the speed of light. Nothing is sent. Something is shared, and it was shared before the particles separated. There is one loophole that cannot be closed by any experiment, and a small number of serious physicists hold it open. Superdeterminism proposes that the measurement settings and the particle properties were correlated from the beginning of the universe, so that experimenters only ever appear to choose freely. Gerard Hooft has defended it. So has Sabine Hossenfelder. It is logically consistent, and it cannot be tested, because any test would use settings that the hypothesis says were prearranged. Bell's own view was that it would make experimental science meaningless, since the entire method depends on being able to vary one thing and see what happens. The reach of these correlations, meanwhile, keeps extending. In 2017, Huan Yin and colleagues used China's Mikyus satellite to send entangled photon pairs down to 2 ground stations 1,203 kilometers apart and confirmed the violation from orbit. The result now holds across continental distances, with the beam passing through the whole depth of the atmosphere twice. There is a family of related results worth knowing about, because Bell's theorem is the famous one, but it is not alone, and the others close doors that Bell leaves ajar. The Cauchy-Specker theorem, proved by Simon Cauchy and Ernst Specker in 1967, makes no reference to distance at all. It shows that you cannot consistently assign definite values to all the measurable properties of a quantum system in advance, even if you allow influences to travel as fast as you like. The values a system appears to have depend on what else is being measured alongside them. This property is called contextuality, and it means the problem is not really about separation between particles. Even a single system, sitting alone on a bench, cannot be described as a collection of properties waiting to be read. Then there is the version that dispenses with statistics entirely. In 1989, Daniel Greenberger, Michael Horn, and Anton Zeilinger described a state of 3 entangled particles for which local realism and quantum mechanics do not merely predict different averages. They predict opposite results for a single measurement. Bell's inequality requires running an experiment many times and comparing correlation strengths. The Greenberger-Horn-Zeilinger argument requires one run. Where the local realist account says the answer must be one thing, quantum mechanics says it must be the other, with certainty, every time. There is also a question that runs the other way, and it is a strange one. Quantum mechanics violates Bell's bound of 2, but it stops at 2.828. It does not go further. In 1994, Sandu Popescu and Daniel Rohrlich pointed out that you can write down hypothetical devices, now called PR boxes, that produce correlations as strong as 4 while still forbidding any signal from being sent. Nothing in the principle of no faster-than-light signaling requires nature to stop where quantum mechanics stops. So the question is not only why the world is more correlated than Einstein expected, it is also why it is less correlated than it is allowed to be. Nobody has a settled answer. Bell's theorem has also stopped being purely a subject of study and become a product. If two separated devices violate a Bell inequality, then no pre-existing instruction set can have determined their outputs, which means those outputs are genuinely unpredictable rather than merely hard to predict. Certified random number generation now uses exactly this, and the National Institute of Standards and Technology has run a public randomness service built on it. A theorem written on unpaid leave in 1964 about whether Einstein was right is now used to guarantee that a string of bits was not written down in advance by anybody. Entanglement itself has turned out to be stranger than the original argument required. In entanglement swapping, two pairs are created independently, and one particle from each pair is brought together and measured jointly. The result is that the two remaining particles, which were created separately, never interacted and have never shared a light cone, end up entangled with each other. The correlation is established retroactively, in the sense that it applies to particles whose histories contain no common event other than the measurement that linked them. Two technical points, since this entry rests on them. The detection loophole mattered enormously in the early photon experiments because detector efficiencies were low, sometimes only a few %, so the great majority of pairs were never registered. Drawing a conclusion from the detected minority requires assuming that the detected pairs are representative of all of them, which a sufficiently clever hidden variable theory could arrange to be false. That is why the 2015 results mattered so much. With electron spins in diamond, essentially every event is registered. And aspect switching, remarkable as it was for 1982, was fast but quasi-periodic, rather than genuinely random. The switches ran on a driven acoustic wave, which is unpredictable in practice but not in principle. The experiments of 2015 used random settings generated after the entangled pair was created, and the cosmic Bell test replaced the generator with the universe. It is worth pausing on what it took to arrive here. Bell wrote his paper in a field that was actively discouraged, and he was clear about his own sympathies. He found the quantum picture uncomfortable and hoped that a deeper, more ordinary theory would be found underneath it. Clauser built the first apparatus in the same spirit and has said the result was not what he wanted. Aspect began his doctoral work on the problem after reading Bell's paper while teaching in Cameroon and was told by senior colleagues that it was a poor use of a career. Three men spent decades trying to restore common sense to physics. Between them, they built the apparatus that ruled it out, and they were right about the importance of the question and wrong about the answer, which is a rarer and more useful thing to be than most careers ever manage. So the position at number 5 is unusually firm for a list like this one. The most carefully checked experiment in the history of physics, run with photons and electrons and diamonds and satellites and quasars and 100,000 strangers playing a video game, says that the everyday assumption that things simply have properties, whether or not anyone is looking, is not how this universe is built. Properties, then, are not sitting there waiting. The next entry asks whether the space they were supposed to be sitting in has as many dimensions as it appears to. Number 4. Everything inside may be a projection of information written on a boundary. This one takes away depth. Not the room you are in, and not the distance across it, but the assumption that the third dimension is a fundamental feature of the universe, rather than a very good way of organizing something that is actually stored with one dimension fewer. It is the most technically established idea on tonight's list that most people have never heard of. It has an exact mathematical example. It has a fit to real satellite data, and it began with a question about a cup of tea. In the early 1970s, at Princeton, John Wheeler asked his graduate student a question that was meant as a provocation. Suppose you pour a cup of hot tea into a black hole. The tea has entropy. Entropy, according to the second law of thermodynamics, never decreases in a closed system. But the tea is now behind an event horizon, and everything outside can measure only 3 things about a black hole: its mass, its charge, and how fast it spins. The entropy appears to be gone. Has the second law of thermodynamics just been broken by the simple act of pouring? The student was Jacob Bekenstein, and his answer, published in 1972 and 1973, is the seed of everything in this entry. The entropy is not gone, he argued. It has been added to the black hole, because a black hole must have entropy of its own. And then came the part that changed physics, that entropy is proportional to the area of the event horizon. Not the volume, the area. Every other system in nature has entropy proportional to volume. Double the volume of a gas at the same density, and you double its entropy, because entropy counts microscopic arrangements, and there are twice as many places to put things. A black hole does not work that way. Double its radius, and the entropy goes up by a factor of 4, not 8. The information content scales with the surface, as though the interior were not doing any independent bookkeeping at all. Stephen Hawking's first reaction was that Bekenstein was wrong, and he set out to prove it. What he found instead, in 1974, was that black holes radiate. They have a temperature, and anything with a temperature has entropy, which meant Bekenstein was right. Hawking then fixed the constant that Bekenstein had left open. The entropy is exactly 1/4 of the horizon area, measured in Planck areas. There is that phrase again. The Planck area pixel, which at number 7 was the thing 3 separate experiments failed to detect, is here doing real work in an equation that nobody disputes. The same unit, now load-bearing. The numbers involved are worth stating because they show how far the surface accounting departs from intuition. A black hole of 1 solar mass has entropy of order 10 to the 77th in natural units. The star that collapsed to make it had entropy around 10 to the 58th. Collapsing a star into a black hole multiplies its entropy by a factor of about 100 million. The most information-dense object in the universe is the one with no interior structure anyone can describe. Gerard Hooft took the next step in 1993 in a paper on dimensional reduction in quantum gravity. His suggestion was that this is not a peculiarity of black holes. It is a statement about regions of space in general. The maximum amount of information that can be contained in any region scales with the area of the surface that encloses it, not with the volume inside. Leonard Susskind gave the idea its name and its sharpest formulation in 1995 in a paper published in the Journal of Mathematical Physics titled "The World as a Hologram." The claim is that a three-dimensional world with gravity in it can be described completely by data living on a two-dimensional surface, in the way that a hologram stores a three-dimensional image on a flat piece of film. The obvious objection is why the universe would bother respecting such a limit, and the answer is the most satisfying part of the argument. It does not have to bother. Gravity enforces it. Suppose you wanted to store more bits inside a region than its boundary allows. Information requires physical states, and physical states require energy, and if you concentrate more than a certain amount of energy inside a given radius, the region collapses into a black hole. The moment you try to exceed the bound, the thing you were storing your information in becomes a black hole, whose entropy is exactly the bound you were trying to beat. The limit is not a rule imposed from outside. It is what happens. For 22 years after Bekenstein's paper, this remained suggestive. Then it became exact. In 1997, Juan Maldacena wrote a paper on the large N limit of superconformal field theories and supergravity. It is the most cited paper in the history of high-energy theory, with tens of thousands of citations, and what it provides is a dictionary. On one side of the dictionary is a theory of gravity, with strings and curved space-time and everything that comes with it, in a five-dimensional space with negative curvature called anti-de Sitter space. On the other side is a quantum field theory with no gravity at all, no curved space, no strings, living on the four-dimensional boundary of that space. The two are not similar. They are the same theory. Every question you can ask on one side has an exact translation on the other, and the answers agree. A black hole forming in the interior corresponds to a plasma heating up on the boundary. A particle falling inward corresponds to a disturbance spreading outward across the surface. The interior, with all its depth and geometry and gravitational physics, is completely encoded in a description that has one fewer dimension and does not contain gravity at all. Now the caveat, and it must come immediately, because this is the point at which popular accounts stop being careful. Anti-de Sitter space has negative curvature. It is shaped like a saddle, extended in every direction, and it has a boundary at infinity that behaves like the wall of a box. Our universe does not look like that. Our universe has a small positive cosmological constant, discovered in 1998, which means it is expanding at an accelerating rate, and its geometry curves the other way. Maldacena's correspondence is not a description of the universe we live in. What it is an existence proof. It shows that a universe can be exactly equivalent to a description written with one dimension fewer, and that this is not a metaphor or an approximation, but a mathematical identity. Whether our universe has such a description is unknown. That one can exist is settled, which makes the next result the most interesting piece of evidence on this entry, because someone tried it here. In 2017, Niayesh Afshordi, Claudio Coriano, Luigi Della Rose, Elizabeth Gould, and Kostas Skenderis published a paper in Physical Review Letters called From Planck Data to Planck Era, and the two Plancks in that title are doing different jobs. One is the Planck satellite. The other is the Planck epoch, the first instant of the universe. They took a holographic model of the very early universe, in which the earliest era is described not by inflating space-time, but by a three-dimensional quantum field theory with no gravity in it, and notably, no time. The apparent expansion of the early universe corresponds, in that description, to the flow of energy scales in the field theory, rather than to anything moving. Then they took the predictions of that model for the pattern of temperature fluctuations in the cosmic microwave background and compared them against what the Planck satellite actually measured. The Planck maps contain about 50 million pixels of sky, each one recording the temperature of the oldest light in the universe to a precision of a few millionths of a degree. The holographic model fitted the data. Across a wide range of angular scales, it was competitive with the standard model of cosmology, and it did so without requiring an inflaton field, which the standard picture needs and has never detected. It is not a clean victory. The fit degrades at the largest angular scales, below a multipole of about 30, where the model's approximations break down, and its supporters say so. But for the first time, a holographic description of our own universe was put next to a real dataset and did not fail. Two more results fill in the picture, and both connect this entry to the one below it. In 2006, Shinsei Ryu and Tadashi Takayanagi found a formula that turns the whole idea into arithmetic. Take a region of the boundary theory and ask how entangled it is with the rest. The answer, they showed, equals 1/4 of the area of the smallest surface in the interior that hangs from the edge of that region. A quantity about information on the surface equals a quantity about geometry inside. That equation is now the workhorse of the entire field. And in 2015, Ahmed Al-Mehri, Shi Dong and Daniel Harlow showed how the encoding actually works, and the answer is one that any engineer would recognize. The interior is stored on the boundary the way a quantum error-correcting code stores data, redundantly, smeared out, so that no single small piece of the boundary contains any particular piece of the interior, and damaging part of the surface does not delete part of the room. The innermost interior is only recoverable from a large enough portion of the boundary all at once. It is the same principle that lets a scratched compact disc still play. There is one more thing this framework appears to have done, and it is the oldest open problem in the subject. In 1976, Hawking argued that black holes destroy information outright, which contradicts quantum mechanics at the most basic level, because quantum evolution never destroys anything. The disagreement lasted decades. The resolution requires that the entropy of the radiation coming out of a black hole should rise for a while and then fall back to zero as the hole finishes evaporating, a shape known as the Page curve after Don Page's analysis in 1993. In 2019 and 2020, several groups succeeded in calculating that curve, using techniques built directly on the entanglement geometry machinery described above, involving regions called islands and configurations called replica wormholes. The curve came out. The information appears to come back out with the radiation. Holography is currently the framework in which the longest-running paradox in gravitational physics looks like it is closing. Before the image, there are 4 developments worth adding, because they show how far this idea has spread from the black hole it started in. The first is that Bekenstein's bound can be stated without any black hole in it at all. In its general form, it says that the entropy of any region is limited by a quantity proportional to the region's radius multiplied by its total energy. That is a statement about a bookshelf, a planet, or a person, and it holds for all of them. For an object the size and mass of a human being, the bound works out at something like 10 to the 45th bits, which is a number no storage technology will ever approach, but it is finite, and it is set by the surface rather than by the interior. There is a largest possible amount that can be known about you, and it is decided by how big you are around the outside. The second is that the bound survives being taken out of the laboratory and into cosmology, which was not obvious. In its simple form, the area law fails in an expanding universe, because surfaces are moving and light cannot always be traced the way the derivation assumes. Raphael Bousso fixed this in 1999 with what is now called the covariant entropy bound. Instead of counting entropy on a surface, he counts it on sheets of light that converge inward from that surface, which is a statement that continues to make sense no matter what the geometry is doing. The bound has held up against every attempt to violate it since. The third is a fight that ran for 20 years and is worth telling because it shows the field arguing with itself in public. Leonard Susskind proposed in 1993 that the way to reconcile the outside view of a black hole with the inside view is to accept that they contradict each other and that no single observer can ever check both. An astronaut falling experiences an unremarkable crossing and continues inward. An observer watching from outside sees the astronaut slow, redden, spread across the horizon, and eventually radiate back out as heat. Both accounts are correct. There is no contradiction because there is no observer who can compare them, since one of them can never return. Susskind called it black hole complementarity, and the resemblance to the argument at number 6 about facts that hold only relative to a position is not a coincidence. In 2012, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully showed that complementarity was not enough. Their argument, which became known as the firewall paradox, demonstrated that the assumptions could not all be maintained simultaneously, and that one apparently reasonable resolution was that an infalling astronaut meets a wall of extremely high-energy radiation at the horizon and is destroyed there rather than crossing peacefully. Nobody liked that conclusion, including the authors. It reopened the whole subject for a decade, and the island calculations described a moment ago are the current answer to it. The fourth is that the objects at the center of all this have now been photographed twice. The Messier 87 image came in April 2019. In May 2022, the same collaboration released an image of Sagittarius A star, the black hole at the center of our own galaxy, 27,000 light-years away and 4 million times the mass of the Sun. It is a far smaller object than the first one, and much harder to image because the gas around it completes an orbit in minutes rather than days, so the picture changes while you are taking it. The argument in this entry now has 2 photographed subjects rather than a chalkboard. And there is a number for our own situation that follows directly from the area law, and it is the largest number in this entry. The observable universe is bounded by a cosmological horizon, the surface beyond which light has not had time to reach us. Apply the same accounting to that surface, and its area corresponds to something like 10 to the 122nd Planck areas. On the holographic reading, that is the total information capacity of everything we can ever see, every galaxy, every star, every atom, every event in the history of all of them, with a very large amount of room left over. There is one last consequence, and it is the one that reaches furthest. If the area law is fundamental, then gravity may not be a fundamental force at all. Ted Jacobson showed in 1995 that Einstein's field equations, the central equations of general relativity, can be derived by assuming the area law holds for every small patch of horizon that any accelerating observer could construct, and then applying ordinary thermodynamics. He did not assume gravity and derive thermodynamics. He assumed thermodynamics and derived gravity. That result has an unsettling implication. Deriving the equations of a force from thermodynamics is exactly what happens when the force is not fundamental. Nobody derives the behavior of a gas from first principles and concludes that pressure is a fundamental force. Pressure is what a very large number of molecular collisions look like when you stop tracking the molecules. Jacobson's derivation suggests gravity may be the same kind of thing, not a fundamental interaction, but the statistical behavior of whatever is actually being counted on those surfaces. Eric Verlinde pushed the idea further in 2011, proposing that gravity is an entropic force in the same sense that the elasticity of a rubber band is entropic, arising from the tendency of a system to move towards states it has more ways of being in. His version remains contested, and its predictions for galaxy rotation have had a mixed record against the data. But the underlying observation that the equations of gravity keep turning out to be derivable from information-theoretic assumptions has not gone away, and nobody has explained it away either. Now, the image to hold from this entry. Picture the object photographed in April 2019 at the center of the galaxy Messier, 8755 million light-years away. 6,500 million times the mass of the Sun. Its event horizon is about 40,000 million kilometers across, which is wider than the orbit of Neptune by a factor of 10. It took 8 radio telescopes on 4 continents, operating as a single instrument, the width of the Earth, to produce the image, and what the image shows is a ring of light around a shadow. Stand at a safe distance and consider what has fallen through that surface over 13,000 million years. Gas clouds. Stars, whole and intact, pulled apart on the way in. Dust, radiation, other black holes. Anything that came too close over the entire history of the galaxy. None of it is retrievable, and that is not what is being claimed. What is being claimed is that none of it is gone. Every bit of information about everything that ever crossed that boundary is, in principle, encoded on the surface you are looking at, written in units of the Planck area, at a density of about 1 bit per 4 of them. The surface of that shadow carries something like 10 to the 97th bits. Not a record of the objects. The objects, in the only description that is complete. And if you Hooft and Susskind are right, that is not a special property of black holes. It is the general rule, and every region of space, including the one you are lying in, is subject to it. Which brings back a number from the very beginning of tonight's list. 130 million photoreceptors, reduced to 1 million fibers before the signal has left the eye. At number 10, that was a fact about a limited biological sensor, and the lesson was that your interface compresses the world. Here, the same operation appears to be running one level further out. It may not be only your eye that stores an interior on a smaller surface. It may be the universe, and there may be no version of the interior anywhere that is not stored that way. What this entry does not say is that the room is fake. Nothing here suggests illusion. The room is exactly as real as anything is. What it says is that the room's contents may be a faithful reconstruction of a record kept somewhere with 1 dimension fewer than the room appears to have, and that from inside the room there is no measurement that could tell the difference, because the measurement would be part of the reconstruction. If depth can turn out to be bookkeeping, there is one more thing in that picture worth questioning. The next entry takes away distance itself. Number 3. Space itself may be made out of entanglement. This one takes away distance. Not the contents of space, which the previous entries have already dismantled, but the container. The proposal here is that space is not a stage on which things happen. It is a structure that emerges from how much the parts of a quantum system know about each other, and distance is a measure of how little they know. The idea has a beginning that is unusually easy to date, because it started with an essay that a journal turned down. Mark van Ramsdonk at the University of British Columbia wrote a short paper in 2010 called Building Up Spacetime with Quantum Entanglement. It was rejected. He entered it into the Gravity Research Foundation's annual essay competition instead, where it won second prize, and it was published in General Relativity and Gravitation. It is now one of the most influential short papers in the field, and its central argument is simple enough to follow all the way through without any mathematics. Start with the dictionary from the previous entry. A gravitational interior encoded on a boundary. Now take 2 separate copies of the boundary theory, sitting side by side, not interacting. If the 2 copies are completely independent, the dictionary says you have 2 separate universes. Two interiors, with no connection between them, no way to travel from one to the other, no shared geometry. Now entangle them. Not by sending anything between them, simply prepare the pair in an entangled state of a particular kind. Maldacena had shown in 2001 that the corresponding interior is a familiar object, two black holes joined by a wormhole, the eternal black hole geometry that Einstein and Nathan Rosen wrote down in 1935. So maximum entanglement corresponds to a connected geometry. Zero entanglement corresponds to two disconnected universes. Van Ramsdonk's move was to ask what happens in between, and to do it gradually. Reduce the entanglement a little. The wormhole connecting the two sides becomes narrower and longer. Reduce it further, and the throat narrows further still, and the two regions become harder to reach from each other, and the distance between them in the geometry grows. Keep going. The connection thins to almost nothing. And when the entanglement reaches zero, the throat pinches off entirely, and the two spacetimes separate into two universes with no geometric relationship at all. The conclusion is difficult to unsee once you have seen it. The reason two regions of space are next to each other is that their quantum degrees of freedom are entangled. Spatial connectedness is not a background fact that entanglement happens within. Spatial connectedness is what entanglement looks like from inside. 3 years later, Juan Maldacena and Leonard Susskind gave the idea its slogan in a paper called Cool Horizons for Entangled Black Holes. The slogan is written as an equation with letters where the numbers should be. ER equals EPR. ER is Einstein-Rosen, the wormhole paper of 1935. EPR is Einstein-Podolsky-Rosen, the entanglement paper of 1935, which we met at number 5. Their proposal is that these are not two phenomena. They are one phenomenon, described in two languages, and every entangled pair is connected by a wormhole so small and so non-traversable that it has no geometric description worth the name. Now hold the year. 1935. Einstein published both of those papers within a few months of each other, in the same year, from the same office at the Institute for Advanced Study, with the same collaborator on both. Nathan Rosen's name is on both. Einstein regarded the wormhole paper as a mathematical curiosity, a solution he found interesting and did not expect to correspond to anything. He regarded the entanglement paper as the most serious objection he ever raised, the argument that would eventually show quantum mechanics to be an incomplete description of a deeper and more reasonable reality. He spent the last 20 years of his life on that objection. It was, in a sense, the thing he was still working on when he died. 78 years later, the proposal on the table is that his curiosity and his objection were the same idea, seen from two sides, and that if he had put the two papers next to each other, he might have found the connection himself. He did not. Nobody did for the better part of a century. Both papers outlived him by decades before anyone thought to lay one on top of the other. The slogan on its own would be a nice story. What makes this entry belong at number 3 is that the arithmetic exists. The Ryu-Takayanagi formula, which we met a moment ago, is the quantitative version. Entanglement entropy on the boundary equals 1/4 of a minimal surface area in the interior. Entanglement, measured in bits, equals geometry, measured in square meters. Change one and the other changes, and the relationship is exact rather than analogous. Then, in 2012, something arrived from a completely different field and fitted without being asked to. Brian Swingle was working on tensor networks, which are a computational technique developed in condensed matter physics for handling quantum systems with enormous numbers of interacting particles. One of these, called the multiscale entanglement renormalization ansatz, works by building the state up in layers, each layer describing correlations at a larger scale than the one below it, so that short-range detail is dealt with at the bottom and long-range structure at the top. Swingle noticed that if you draw the network out as a graph and ask what its geometry is, the answer is hyperbolic space. The layers behave like a radial direction. The network, invented purely to make a calculation tractable on a computer, has the shape of the interior of an anti-de Sitter spacetime. Nobody put that there. It is what fell out of organizing quantum entanglement efficiently, and it is one of the more suggestive accidents in modern physics. At which point some people in the field stopped treating spacetime as the starting assumption at all. Nima Arkani Hamed has spent 15 years saying, in talks and papers, that spacetime is doomed, and he means it technically, that locality and unitarity, the two properties every physics course begins with, are approximations that emerge from something more basic and are not fundamental. The evidence he points to comes from the mathematics of particle collisions. In 2013, with Jaroslav Trnka, he introduced an object called the amplituhedron. It is a geometric shape, defined in an abstract space, and the probability of a given particle interaction is computed as its volume. There is no space in the definition. There is no time. Locality never appears, and neither does the sequence of events that a Feynman diagram represents. And yet the answers come out right, and they come out in a single expression, where the traditional method would require thousands of separate diagram terms that then cancel against each other almost entirely. That cancellation had been the clue for years. Physicists had noticed that scattering calculations produced pages of terms that collapsed into something short and simple, which normally means the method being used is not the natural one. The Brito-Cacciazzo-Feng-Witten recursion relations of 2005 had already shown that amplitudes could be built up without space-time locality appearing anywhere in the construction. The amplituhedron is the geometric version of the same suspicion. Now the honest limitation, and it is a serious one. All of this is exact only in anti-de Sitter space. Every result quoted in this entry, from Van Ramsdonk's dial to the Ryu Takayanagi formula to the error-correcting code, is established in a universe with negative curvature and a boundary at infinity. Our universe has positive curvature driven by dark energy and no such boundary. There is no established version of any of this for the space we actually live in. People have been trying for 2 decades. It is generally regarded as the central open problem of the subject. So this entry is a research program of remarkable internal consistency with no direct observational test, and it would be dishonest to present it as anything else. It is also a subject with a recent object lesson in overclaiming, and the lesson is worth including. In 2022, a paper appeared reporting that a wormhole had been created and traversed on Google's Sycamore quantum processor. It was covered widely, in terms suggesting that a hole through spacetime had been opened in a laboratory in California. What had actually been done was a 9-qubit simulation of a heavily simplified toy model on hardware, producing a signal consistent with the model's predictions. Criticism from inside the field was immediate and substantial. No wormhole was made. No spacetime was involved. What was demonstrated was that a small quantum computer can simulate a small quantum system, which is what quantum computers are for. The model underneath that experiment is real, though, and it is doing serious work. The Sachdev-Yekitaev model describes a collection of fermions interacting with each other at random, and it is unusual in being solvable while also reproducing the behavior of the region just outside a black hole horizon. In 2016, Maldacena, Stephen Schenker and Douglas Stanford showed that it scrambles information at the maximum rate any quantum system is permitted to reach, and that black holes reach the same maximum. Whatever a black hole is doing to information, an abstract model of randomly interacting particles does it just as fast. There is a set of supporting observations behind all of this that make it less like a slogan and more like a research field, and they are worth walking through slowly, because each one is a place where entanglement and geometry turned out to be measuring the same thing. Start with a fact about ordinary quantum field theory that has nothing to do with gravity. Take any region of space in a typical field theory in its lowest energy state and ask how entangled the contents of that region are with everything outside it. The naive expectation is that the answer scales with the volume of the region, because entanglement is carried by the particles inside, and there are more of them in a bigger box. The actual answer scales with the area of the region's boundary. The entanglement lives on the surface because it is carried by correlations that reach across the boundary, and only the parts near the boundary can do that. That is the same scaling as black hole entropy, arrived at in a completely different way, in a theory with no black holes in it. It is one of the reasons people took the connection seriously before there was any dictionary to make it precise. Next, consider what the interior is doing when nothing appears to be happening. A black hole reaches thermal equilibrium quickly, in the sense that everything an outside observer can measure about it settles down. But in the two-sided picture, the wormhole between the two black holes keeps growing for an enormously long time after equilibrium is reached. Something inside continues to change while every external quantity has stopped changing. Susskind's proposal, usually stated as complexity equals volume, is that what the growing interior is tracking is the computational complexity of the boundary state. How many elementary operations would be needed to build that state from a simple starting point? Complexity keeps rising long after entropy has saturated, and it rises for about as long as the wormhole keeps growing. If that identification holds, then the size of a region of spacetime corresponds to the difficulty of a computation. The scale of the effort behind this is worth noting too. In 2015, the Simons Foundation funded a collaboration called It from Qubit, which brought quantum information theorists and gravitational physicists into a single program with the explicit aim of working out whether spacetime is made of entanglement. The name is a deliberate reference to John Wheeler's Phrase It from Bit from 1989, in which he proposed that every physical thing derives its existence from answers to yes or no questions. Wheeler was making a philosophical gesture. The collaboration was set up to check whether the gesture had equations behind it. There is also an older ancestor to this whole way of thinking, and it belongs to Roger Penrose. In 1971, he introduced spin networks, graphs whose edges carry units of angular momentum and whose nodes represent ways of combining them. His aim was to build up the appearance of three-dimensional space and its angles purely from combinatorial relationships between quantum numbers, with no space assumed at the start. Directions were to emerge from the network rather than the network being drawn in space. Spin networks became the mathematical backbone of loop quantum gravity, which we met at number 7, and they are the direct ancestor of the idea that geometry is a bookkeeping device for relationships rather than a container for them. One consequence of the entanglement picture is worth stating in its bluntest form, because it is the part that reorganizes intuition most thoroughly. In this language, a maximally entangled pair of quantum bits is adjacent. Not near each other in the ordinary sense, adjacent in the structure from which nearness is built. Two atoms sitting a meter apart on a bench, with no entanglement between them, are in the relevant sense further apart than a pair of entangled particles at opposite ends of the galaxy. The meter is real. It is simply not the fundamental quantity, and it is not the one that decides whether two things are connected. And the machinery has now done something no framework does unless it is at least partly right. It produced a result that its authors did not put in by hand. The island calculations of 2019 and 2020, which resolved the black hole information problem at the level described in the previous entry, were carried out using exactly this entanglement geometry apparatus. Nobody wrote down the page curve and worked backwards to it. The calculation was set up, the minimal surfaces were computed, and at a certain point in the black hole's evaporation, a new surface, located inside the hole, becomes the smaller one and takes over. When it does, the entropy of the radiation stops rising and begins to fall, which is precisely the shape that unitarity requires and that Hawking's original calculation could not produce. The answer came out of the geometry. There is one more structural feature that deserves a sentence, because it explains something otherwise strange about the encoding. In the error-correcting code picture, the deepest part of the interior is the most thoroughly protected and the hardest to reach. No small piece of the boundary contains it. You need a substantial fraction of the whole surface before the center of the interior becomes recoverable at all. Which means that in this framework, the center of a region of space is not stored anywhere in particular. It is stored in the relationships among a large number of places, none of which contains it. Depth, in the holographic dictionary, is a measure of how spread out something is on the surface. And the last piece connects back to gravity itself. If space is built from entanglement, and the equations of gravity can be derived from thermodynamics applied to surfaces, then the two statements are the same statement. Ted Jacobson's derivation in 1995 assumed the area law for local horizons and produced Einstein's field equations. Van Ramsdonk's argument starts from entanglement and produces connected geometry. Between them, they suggest that what we call gravity is what a very large amount of quantum correlation looks like when it is coarse-grained into a shape, in the same way that temperature is what a very large amount of molecular motion looks like when it is coarse-grained into a number. That is either a coincidence of unusual size, or it is the reason general relativity and quantum mechanics have refused to combine for 100 years. They may have resisted because one of them is not fundamental, and the wrong one has been treated as the foundation. Which returns us to a sentence from number 9 and inverts it. You have never touched anything. At number 9, that was a statement about a gap, the electromagnetic fields of two sets of electrons pushing against each other across a space that never closes, so that contact is a force law rather than an event. On the picture in this entry, the gap was never the point. If space is built from entanglement, then two things being close is not a matter of the distance between them being small. It is a matter of their quantum states being strongly correlated. Touch, in that language, is not about closing a gap. It is about correlation, and the correlation is real whether or not anything ever meets. And it means the universe is not large because it is spread out. It is large because most of it is uncorrelated with most of the rest of it. Distance is not a stage that has to be crossed. It is a measure of how little two places have in common. Space, taken apart, which leaves the observer standing in it. And the next entry asks whether that observer has a past. Number 2, the arithmetic says you are more likely a fluctuation than a person. This one takes away your own standing. Every entry so far has removed something about the world and left the observer in place. Number 2 removes the observer's claim to be an ordinary one, with a real past, in a universe that has been running for 13,800 million years. It is the only entry on tonight's list that is generally regarded as a problem rather than a discovery. Physicists do not defend this conclusion. They try to get out of it, and the ways they have found are as interesting as the argument itself. It begins with a letter, and the letter is 131 years old. In 1895, Ludwig Boltzmann wrote to the journal Nature about the direction of time. He had spent his career arguing that the second law of thermodynamics is statistical rather than absolute, that entropy increases not because it must, but because there are overwhelmingly more disordered arrangements than ordered ones, so a system wanders into disorder simply by wandering. The problem with that view is that it makes the low entropy past a puzzle. If the universe is just wandering, why was it ever ordered enough for anything to happen? Boltzmann floated an answer, attributing it to an assistant, and the answer was that maybe the universe as a whole is already in equilibrium, everywhere, and has been forever. Equilibrium is not perfectly static. Things fluctuate. Occasionally, somewhere, a region will fluctuate into a state of much lower entropy purely by chance, and then relax back. We might be living inside such a fluctuation, in a corner of an otherwise featureless universe, watching our accidental order run down. It is a clever idea, and it is almost certainly wrong, and understanding exactly why it is wrong is what gives this entry its shape. Fluctuations are suppressed exponentially with size. A small deviation from equilibrium is unlikely, a larger one is very much more unlikely, and the relationship is not gentle. So if you are a fluctuation, the question is what the cheapest fluctuation is that could account for what you are experiencing right now. The answer is not a universe. It is not 13,800 million years of history, 93,000 million light-years of space, 2 million galaxies, a sun, a planet, an evolutionary record, a childhood, and a set of physical laws that hold everywhere. The cheapest fluctuation consistent with your present experience is a single brain, assembled at random out of the surrounding chaos, complete with a full set of memories that never happened, having the experience you are having right now, and dissolving a few seconds later. That entity has a name. It is called a Boltzmann brain. Arthur Eddington made the objection to Boltzmann's version in 1931, and Richard Feynman repeated it in his lectures in 1964, and the objection is not philosophical. It is a working scientific test, and it is one of the more elegant tests anyone has devised. If you are a fluctuation, then you should not expect to find order anywhere you have not already looked. The fluctuation only had to produce the parts you have experienced. Anything beyond that is additional cost, and additional cost means additional improbability. So every time a new telescope is pointed at a fresh patch of sky, and that patch turns out to be lawful, full of galaxies obeying the same physics as everything else, the fluctuation hypothesis takes a hit. Every survey ever conducted has come back lawful. Boltzmann's version of the idea fails that test spectacularly and continuously, and has done so for a century, which would close the entry, except that the modern version does not come from a thought experiment. It comes from a measurement. In 1998, 2 independent teams surveying distant supernovae found that the expansion of the universe is accelerating. That result implies a positive cosmological constant, an energy density belonging to space itself, which does not dilute as space grows. It has been confirmed many times since, and it earned a Nobel Prize in 2011. Now follow the consequence forward. If the cosmological constant is genuinely constant, then as the universe expands, everything else thins out, and eventually the dark energy is all that is left. The universe approaches a state called de Sitter space, empty, expanding exponentially, with a horizon around every observer. And in 1977, Gary Gibbons and Stephen Hawking showed that such a space has a temperature. The horizon radiates, in the same way that a black hole horizon radiates, and for the same reason. For our measured expansion rate, that temperature comes out at about 2.7 times 10 to the minus 30 Kelvin. It is worth pausing on how small that is. The cosmic microwave background, the coldest thing filling the sky, sits at 2.7 Kelvin above absolute zero. The de Sitter temperature is that number divided by 1,000 million. The coldest laboratory on Earth has reached temperatures of a few hundred picokelvin, and the de Sitter temperature is colder than that by a comparable factor again. It is, for every practical purpose, zero. But it is not zero. And that is the whole entry. A non-zero temperature means thermal fluctuations. Thermal fluctuations sustained over infinite time means that anything not strictly forbidden will happen, and will happen infinitely often, including the spontaneous assembly of an ordered region containing a functioning brain with false memories. The estimated waiting time for such an event is of the order of e raised to the power of 10 to the 69th years. That number cannot be written down and cannot be pictured, and the usual comparisons fail entirely because the exponent by itself already exceeds the number of atoms in the observable universe. It is not a long time. It is a number that has no relationship to the concept of a long time. But it is finite. And the future of a de Sitter universe, on current physics, is not finite. Divide infinity by any finite number, and the answer does not get smaller. So the count of fluctuation observers, integrated over the whole future, is unbounded. The count of ordinary observers, born from the low-entropy Big Bang during the finite window in which stars and planets and chemistry exist, is a large but finite number. And if you are told to reason as a typical member of the set of all observers with experiences like yours, the arithmetic points somewhere unpleasant. The paper that turned this into a working problem was published in 2002 by Lisa Dyson, Matthew Kleben, and Leonard Susskind, under the title Disturbing Implications of a Cosmological Constant. It set out plainly that a universe with the dark energy we have measured eventually produces more accidental observers than real ones. Andreas Albrecht and Lorenzo Sorbo followed in 2004, and Raphael Busso and Ben Freivogel in 2007, and the problem has been in the literature ever since. The technical obstruction that keeps it open is called the measure problem, and it deserves a sentence because it is why nobody has simply settled the matter with a calculation. In an eternally inflating universe, both populations are infinite. Comparing two infinite sets requires a rule for how to count them, and the answer you get depends entirely on which rule you choose. Different, reasonable-looking rules give opposite answers. There is no agreed rule, and there has not been one for 25 years. Which brings us to the response that carries this entry, and it is not a reassurance. Sean Carroll published a paper in 2017 titled Why Boltzmann Brains Are Bad. His argument is that the correct response to a theory predicting you are most likely a random fluctuation is not fear. It is disqualification. Such a theory, he points out, is cognitively unstable. If it is true, then your memories are fabricated, your reasoning was assembled at random, the textbooks you learned physics from never existed, and the observations supporting the theory were never made. Which means the evidence for the theory is worthless, including the evidence that led you to it. The theory cannot be simultaneously true and justifiably believed. It undermines the grounds of its own acceptance. Carroll's conclusion is that this counts as a legitimate reason to reject a cosmological model, in the same way that an internal contradiction is a reason to reject it. A model that predicts Boltzmann brains dominate is not frightening. It is disqualified, and physicists should go and build a better one. Sit with the shape of that for a moment, because it is unusual. The only defense physics currently offers against this conclusion is that believing it destroys the reasoning that produced it. That is a strange kind of shelter. You are safe from the conclusion, but only because if the conclusion were true, the argument for it would be worth nothing. It does not tell you that you are a real person with a real past. It tells you that the question cannot be answered by anyone in a position to ask it. There is also a technical route out, and it may be the right one. In 2016, Kimberly Boddy, Sean Carroll, and Jason Pollock argued that the whole problem may rest on a category error. Fluctuations, in the everyday sense, are things that happen to a system over time. But a de Sitter vacuum, treated fully quantum mechanically, without any measurement or collapse imposed on it, is a stationary state. A stationary state does not do anything. It has a non-zero overlap with brain-like configurations, in the sense that the mathematics assigns them a non-zero amplitude, but nothing ever actually occurs. On that reading the fluctuation, observers never come into existence at all, and the problem dissolves rather than being solved. And there is a clock that may cut the whole thing short. The Standard Model's vacuum may not be permanent. Given the measured mass of the Higgs boson, near 125 gigaelectronvolts, and the measured mass of the top quark, the electroweak vacuum sits in what is called a metastable region, not the lowest possible energy state, but separated from it by a barrier. Sidney Coleman and Frank DeLucia worked out the gravitational version of such a decay in 1980. The expected lifetime runs far past 10 to the 100th years, which is much longer than the universe has existed, and much longer than it will take to go dark. But it is not infinite, and if the vacuum decays before the fluctuation clock runs out, the fluctuation clock never finishes. There is a timeline underneath all of this, and it is worth laying out, because the argument depends entirely on how much future there is. Star formation in the universe is already past its peak, and will effectively finish within about 100 million years, once the gas available for making new stars is exhausted. The longest-lived stars, the small red dwarfs, will keep burning for something like 10 million years after that, which is roughly 1,000 times the current age of the universe. When the last of them cools, the universe becomes dark in the ordinary sense, and everything remaining is a remnant, white dwarfs cooling toward the background temperature, neutron stars, and black holes. Whether the matter in those remnants survives depends on whether protons decay, which is one of the genuinely open questions in physics. The Super Kamiokande detector in Japan, 50,000 tons of ultra-pure water watched by more than 11,000 photomultiplier tubes a kilometer underground, has been looking for a single proton to fall apart since 1996. It has not seen one, which sets a lower bound on the proton lifetime past 10 to the 34th years. If protons do decay somewhere beyond that bound, ordinary matter eventually evaporates. If they do not, the remnants persist. The black holes go last, and they go slowly. A black hole of a few solar masses takes something like 10 to the 67th years to radiate itself away. The largest known supermassive black holes, tens of thousands of millions of solar masses, take of order 10 to the 100th years. After that, there are no objects of any kind. And even that is not the end of the arithmetic. For a closed system with a finite number of states, there is a time after which it returns arbitrarily close to any configuration it has previously been in. It is called the Poincaré recurrence time, and for a system the size of the observable universe, the estimate is around 10 to the power of 10 to the 120th years. It is the largest number that appears anywhere in serious physics, and it exists because eternity is long enough for a universe to accidentally reassemble itself. Underneath the whole argument sits an assumption that most of the objections attack, and it should be named. It is called the self-sampling assumption, the rule that you should reason about yourself as though you were a randomly selected member of the relevant class of observers. Without it, the Boltzmann brain argument does not get started, because the fact that most observers are fluctuations tells you nothing about which one you are. With it, the argument follows immediately. Whether the assumption is legitimate is a question philosophers have argued about since the 1980s, and it is exactly the same premise that the final entry on tonight's list depends on. The two top entries stand or fall on the same disputed rule about how to count yourself. The nearest relative of this reasoning is the doomsday argument, which applies the same rule to birth order rather than observer type, and concludes that you should expect to be somewhere in the middle of all humans who will ever live, which puts an unwelcome cap on the future population. It has been in the literature since 1983. Nobody has refuted it, and almost nobody believes it, which is roughly the position the Boltzmann brain argument occupies as well. There is one more piece of evidence that cuts against the fluctuation picture, and it is the strongest one available. The cosmic microwave background is smooth to about 1 part in 100,000 across the whole sky. Two patches of sky on opposite sides of the universe, which have never been in contact, have the same temperature to 5 decimal places. That uniformity is a serious puzzle in its own right, and is the reason inflation was proposed. But it is also a very expensive thing for a fluctuation to produce. A fluctuation that had to account only for your present experience would have no reason to lay down a smooth background across a sky you were never going to survey. The smoothness is exactly the kind of unnecessary order that Eddington's test says a fluctuation should not deliver, and it is measured to 5 decimal places. The other side of the same coin is the number Penrose calculated for how special the beginning was. 1 part in 10 to the power of 10 to the power of 123. That is the improbability of the initial state, and it is the reason the past is a problem in the first place. The universe began in a condition so ordered that no known mechanism accounts for it, and the fluctuation hypothesis was an attempt to explain that away. It fails, and the ordered beginning remains unexplained, which is a fair summary of where cosmology actually stands. Now the picture to hold, because it is where this entry lives. 10 to the 100th years from now. The number of years is a 1 followed by 100 zeros, and the entire history of the universe up to this evening is a rounding error against it. Every star has burned out. Every remnant has cooled. Every galaxy has either been swallowed by its central black hole or evaporated into isolated wandering objects, and the black holes themselves have finished radiating away and are gone. There is no matter arranged into anything. There is no chemistry. There is nothing anywhere that could be called an event. What remains is space, expanding, and around every point in it, a horizon at a fixed distance, glowing very faintly. The temperature at that horizon is 3/10,000 million millionths of a degree above absolute zero. And it does not stop. There is no next stage. That is the final condition of the universe on current physics, and it continues at that temperature without any limit at all. Whatever the arithmetic of rare events implies, this is the era in which it has room to operate. One last figure, from a different direction, because it belongs here. In an infinite flat universe with the same physical laws throughout, a finite volume can contain only a finite number of distinct quantum states, which means arrangements must repeat. Standard estimates put the nearest exact copy of a given observer in a universe like that at around 10 to the power of 10 to the 29th meters away. It is not a metaphor, and it is not a thought experiment. It is arithmetic, applied to an assumption about infinity that cosmology currently takes seriously. So the standard scientific reply to number 2 is not comfort. It is a rule. Any cosmology that predicts you are probably a fluctuation is thereby disqualified, because such a theory eats its own evidence. Every entry on this list so far has removed something and left the rest standing. The last one removes what the rest were standing on. Number 1. The simulation argument, and the reason it cannot be closed from inside. This one takes away the base level. Everything the previous 9 entries left standing, including the assumption that there is a bottom to reality at all, and that whatever it is the thing that is actually happening rather than a description of something else. It is also the entry most people arrive at this subject through, and almost everybody has it wrong, including a great many people who repeat it confidently in public. So before anything else, the argument needs to be stated correctly, because the correct version is more interesting than the popular one and considerably harder to dismiss. Nick Bostrom published a paper in the Philosophical Quarterly in 2003, having circulated a draft 2 years earlier, titled, "Are You Living in a Computer Simulation?" It does not claim that we are living in a computer simulation. It never claims that. What it establishes is that at least one of 3 propositions must be true, and that we cannot consistently believe all 3 are false. Proposition 1. Almost all civilizations at roughly our stage of development go extinct before reaching a level of technology capable of running detailed simulations of conscious minds. Proposition 2. Almost no civilization that does reach that level chooses to run a significant number of such simulations of its own history. Proposition 3. We are almost certainly living in one. That is the whole structure. It is a disjunction, not an assertion, and its force comes from how unattractive it is to reject any of the 3. The engine underneath it is a counting step, and the counting step is why the argument survives objections about technology. Suppose that civilizations reaching a mature stage do run many detailed simulations of minds like ours, for research, for history, for reasons we cannot guess. Then across the whole population of minds having experiences like the one you are having right now, the simulated ones vastly outnumber the original ones. Not by a little, by whatever ratio the simulating civilization finds convenient, which could be thousands or millions to 1. And if you cannot tell from the inside which kind you are, then the reasonable thing to do is assign your credence in proportion to the population. That is the indifference step, and it is the same rule that appeared at number 2, applied to a different set. The 2 entries at the top of this list depend on the same disputed principle about how to count yourself, which is worth noticing, because it means they are not 2 independent arguments. They are one habit of reasoning, pointed in 2 directions. Notice what the argument does not require. It does not require any particular technology. It does not require that consciousness be computable, though it does assume it, which we will return to. It does not require the simulation to be perfect or complete. It is an argument about populations, and the computing is only there to explain how the population might get large. Still, the computing is worth putting numbers on, because the numbers are surprising. Bostrom's rough estimate for the operations required to simulate the entire mental history of everyone who has ever lived is somewhere around 10 to the 33rd to 10 to the 36th operations. That is an estimate with wide error bars, and it assumes you simulate minds rather than atoms. Set that against the physical ceiling. Seth Lloyd published a calculation in Nature in 2000 of the ultimate physical limits to computation, and the answer for 1 kilogram of matter, organized as efficiently as the laws of physics permit, is about 10 to the 51st operations per second and about 10 to the 31st bits of storage. Those limits come from the speed of light, the quantum of action, and the fact that concentrating too much energy in too small a volume produces a black hole. They are not engineering estimates. They are the walls of the room. On those figures, 1 kilogram of ideally organized matter running for a fraction of a second exceeds Bostrom's requirement by 15 orders of magnitude. The simulation is not hard. If it is possible at all, it is trivially cheap for anyone who can build the hardware. And for perspective on the other side, Lloyd worked out in 2002 what the universe itself has managed. Treating every particle interaction since the Big Bang as a computation, the observable universe has performed at most about 10 to the 120th elementary logical operations on about 10 to the 90th bits. That is the entire computational budget of reality, and it is a finite number. Now the problem that makes this entry difficult, and it has to be faced directly. A sufficiently good simulation is undetectable from inside, by construction. If the simulation includes your instruments, your senses, your memories, and the physical laws you use to check for anomalies, then no observation you make can distinguish it from a base-level universe. That is not a temporary limitation. It is what the word simulation means in this context, which reduces the scientific question to something much narrower and much more answerable. Forget perfect simulations. Ask instead whether our physics shows signs of the specific kind of simulation we already know how to build. That question has been asked properly exactly once, and it produced the only number on this entry. In 2012, Silas Bean, Zore Dawoodi, and Martin Savage circulated a paper called Constraints on the Universe as a Numerical Simulation, published in the European Physical Journal A in 2014. Their approach is admirably concrete, and it starts from what nuclear physicists already do for a living. Lattice quantum chromodynamics is a working technique. To calculate the behavior of quarks and gluons, you replace continuous spacetime with a finite grid of points, put the fields on the grid, and let a supercomputer evolve the whole thing. Present-day lattice calculations handle a cube of nuclear matter a few femtometers across, which is about the size of a small nucleus. The technique produces the proton's mass correctly, as we saw at number 9. So the authors asked the obvious question. If our own physics can simulate a femtometer of universe today, and computing power keeps increasing, then at some point, somebody simulates a much larger volume. What would it look like from inside? The answer is that a grid gives itself away by having axes. A cubic lattice is not the same in every direction. Along a lattice axis, it looks different from the way it looks along a diagonal, in the way that a woven fabric has a grain. Perfect rotational symmetry is the one property a grid cannot have. Ordinary particles, with wavelengths enormously larger than the grid spacing, would never notice. But particles with wavelengths approaching the grid spacing would. They would show a preferred direction, clustering along the lattice axes, and they would run into an energy cutoff imposed by the grid itself. So the test is to look at the highest energy particles in the universe and ask whether their arrival directions know about a grid. From the observed cutoff of the cosmic ray spectrum, the authors derived a bound. The inverse lattice spacing must be greater than about 10 to the 11th giga-electron volts. If there is a grid, it is finer than that. Putting that number in context matters, because on its own it is meaningless. The Large Hadron Collider collides protons at about 14,000 giga-electron volts. The bound sits roughly 10 million times higher than the most energetic machine our species has built, and there is no prospect of building an accelerator that reaches it. This is not a bound we obtained. It is a bound nature handed us, because nature runs a better accelerator. The particles that provided it are worth knowing about, because they are among the strangest objects in astronomy. On the 15th of October 1991, the Fly's Eye detector in the Utah desert recorded a single cosmic ray carrying 3 × 10⁻20 electron volts. One subatomic particle, almost certainly a proton, arriving with roughly the kinetic energy of a briskly thrown baseball. Everything about it was implausible enough that the team spent a long time checking, and it has been known ever since as the "Oh my God" particle. It was traveling at a speed such that, in the 26,000 years it would take light to cross the galaxy, the particle would fall behind by a fraction of a second. More have been found since. In 2023, the Telescope Array Collaboration, also in Utah, announced a second extreme event, detected on the 27th of May 2021, at 2.4 × 10⁻20 electron volts. They named it the Amaterasu particle. Its arrival direction points back at a region of sky containing nothing that looks capable of producing it. There is a complication that makes this test much harder than it sounds, and honesty requires it be included. In 1966, Kenneth Greisen in the United States and Georgy Zatsepin and Vadim Kuzmin in the Soviet Union independently predicted that protons above about 5 × 10⁻19 electron volts cannot travel far. They collide with photons of the cosmic microwave background and lose energy, so that beyond a distance of some hundreds of millions of light-years, the high end of the spectrum is stripped away. That cutoff has been observed by the high-resolution Fly's Eye and by the Pierre Auger Observatory, which means there is already a perfectly ordinary physical reason for the spectrum to end where it does. Disentangling a lattice cutoff from a cutoff caused by the oldest light in the universe is genuinely difficult, and nobody has managed it cleanly. The other half of the signature, the preferred direction, has been looked for, and something was found. It just was not a lattice. In 2017, the Pierre Auger Observatory published in Science a detection of large-scale anisotropy in the arrival directions of cosmic rays above 8 × 10⁻18 electron volts. There is a dipole, an excess in one broad direction across the sky, with an amplitude of about 6.5%. It points away from the center of our galaxy, which is exactly what you expect if the highest energy particles come from outside the Milky Way rather than inside it. It is an important result about where cosmic rays are made. It is not a lattice axis, and no lattice axis alignment has been reported by anyone. So the honest score on the only real test is 1 bound derived, 1 confound in the way, 1 anisotropy found and explained by ordinary astrophysics. 2 other proposals belong here, delivered as what they are rather than as what headlines have made of them. Gerard Hooft's cellular automaton interpretation, which we met at number 7, proposes deterministic computation at the Planck scale underlying quantum mechanics. It is a serious program by a serious physicist, and it has not yet produced a distinguishing prediction. Melvin Vopson published a paper in the journal AIP Advances in 2023 called The Second Law of Infodynamics and its Implications for the Simulated Universe Hypothesis. His claim is that information entropy in certain physical systems decreases over time rather than increasing, and he reads that as evidence of data compression, of the kind a simulation would perform. It received a great deal of coverage. It is one researcher's contested proposal, it is not accepted by the wider field, and it is included here for completeness rather than as evidence. The most careful treatment of the odds themselves came in 2020 from an astronomer rather than a philosopher. David Kipping at Columbia University published a Bayesian approach to the simulation argument in the journal Universe. He formalizes Bostrom's trilemma properly and adds a distinction the original lacks. He divides realities into two kinds: Paraus realities, which have the resources to spawn simulated realities of their own, and nulliparous realities, which do not, because each nested generation inherits a fraction of the computing power of the one above it. The point of the distinction is that it changes the counting. Simulations of simulations get cheaper and poorer as you go down, so the overwhelming majority of simulated realities must be nulliparous ones near the bottom of the stack. When Kipping runs the analysis with that structure included, the physical hypothesis comes out marginally favored. The odds sit close to even, tipping slightly toward this being base reality. And his analysis contains one clean consequence, which is the right place to leave the argument. The odds move decisively toward simulation the moment a civilization demonstrably creates a conscious simulated reality of its own. Because at that point, Proposition 2 is falsified by direct evidence, and the trilemma collapses onto Proposition 3. Which means the only decisive experiment for the last entry on this list is not an observation of the sky. It is something we would have to build, and the answer would arrive as a consequence of a decision we made. The strongest objections deserve room before we finish, because this entry has more of them than any other. Stephen Wolfram's objection is computational irreducibility. For most systems of any complexity, there is no shortcut. The only way to find out what the system does is to run it, step by step, with no compression available. If the universe is irreducible in that sense, then simulating it faithfully costs as much computation as the universe itself, which removes the premise that a mature civilization could run many of them cheaply. Sabine Hossenfelder's objection is more direct. Nobody has demonstrated that it is even possible to reproduce the standard model of particle physics together with general relativity on a computer. Our best theories are not known to be simulable in that way, and putting them on a lattice is known to break some of their symmetries. The argument assumes a capability that has never been shown to exist. And the deepest objection is that the whole thing rests on substrate independence, the assumption that a sufficiently detailed simulation of a mind is a mind and has experiences. That is not established. It may be true. It is one of the oldest open questions in philosophy. It sits directly underneath the counting step, and if it is false, the argument does not get started. Bostrom's own stated position, incidentally, has always been much weaker than the version that circulates. He has consistently said that the three propositions look roughly equally plausible to him, which is a long way from asserting that we are in a simulation. Two more things belong here before the list closes, and the first is about the detectors, because the scale of the effort is part of the argument. Ultra-high energy cosmic rays arrive at a rate of roughly 1 particle per square kilometer per century. That is the entire reason the test at the heart of this entry is so hard. To collect a useful number of events, you need a detector the size of a country, running for decades. The Pierre Auger Observatory in western Argentina covers 3,000 square kilometers of pampas, with about 1,600 water tanks, each holding 12 tons, spaced 1.5 kilometers apart, each watching for the flash of light produced when the shower from a single particle passes through. Alongside them sit fluorescence telescopes that watch the sky on dark, moonless nights for the faint ultraviolet glow of the shower itself as it burns down through the atmosphere. The telescope array in Utah is the northern counterpart, covering about 700 square kilometers. Those instruments were not built to test the simulation hypothesis. They were built to find out where the highest energy particles in the universe come from, which is a question nobody has answered. But they are the only apparatus in existence capable of returning data on the question at all, and the bound of 10 to the 11th giga-electron volts came out of their spectrum. There is a symmetry in that worth noticing. Zorae Davoudi, one of the 3 authors of the lattice paper, has spent the years since working on how to simulate quantum field theories on quantum computers. The same program run forwards. The people asking whether we are inside a simulation of this kind are, in many cases, the same people learning how to build one. The second thing is the set of objections that cannot be tested, and they should be named honestly rather than left as loose ends. The most common is the render-on-demand argument, that a simulation would not compute the whole universe, only the parts currently being observed, in the way a video game generates scenery as a player approaches it. It is offered as an explanation for why we find no computational shortcuts, and it also disposes of the computational cost objection entirely. It is also completely untestable, for the obvious reason that any measurement you make to check is itself an observation, which the hypothesis says triggers the rendering. It explains everything, which means it predicts nothing. Underneath that sits the hardest problem of all. John Searle's Chinese room argument from 1980 holds that running the right computation is not sufficient for understanding, and by extension, not sufficient for experience. A system can produce every correct output without anything it is like to be that system. If Searle is right, then a simulated mind is not a mind. The population of simulated observers is 0, regardless of how many simulations are run, and the counting step at the heart of the argument has nothing to count. Nobody has settled this, and nobody is close to settling it. The entire trilemma is balanced on a question about consciousness that predates computers by centuries. And the argument has had a strange public life, which is worth a sentence because it explains why the careful version is so rarely heard. It was the subject of the 2016 Isaac Asimov Memorial Debate at the American Museum of Natural History in New York, where a panel of physicists and philosophers spent an evening on it in front of a full auditorium. Prominent technologists repeat it regularly, usually in a form far stronger than Bostrom's paper supports, sometimes with confident odds attached that appear nowhere in any published analysis. The detail that gets lost every time is the structure. It is a disjunction. It says at least one of 3 things is true. Convert it into an assertion that one particular branch is true, and you have not strengthened the argument. You have thrown it away and kept the part that sounds best. So we reach the bottom of the list, and it is worth stopping to look back up it. 10 entries. 10 removals. Your senses stopped being a window and became an interface. Solidity became a force law. The passage of time became a property of memory rather than of the universe. The smoothness of space came into question, and 3 searches came back clean. Facts stopped being things that are true for everyone. Properties stopped existing before they are measured. Depth became a possible piece of bookkeeping on a surface. Distance became a shortage of shared information. Your standing as an ordinary observer became a statistical question with no agreed method of counting. And the base level itself became a proposition in a trilemma that cannot be resolved from inside. That is a considerable amount of the world to have removed in one evening. And here is the thing that the whole list was built to arrive at. After every single one of those removals, the universe carried on behaving in exactly the same way. The clocks on the satellites still needed correcting by 38 microseconds a day, and the correction still worked. The interferometers still measured to 1,000th of the width of a proton, and they still found nothing where nothing was predicted and something where something was. The cosmic rays still arrived. The photons from the quasars still set the analyzers. The molecules still interfered. Every measurement in this video was made after the removal it describes, by people who understood exactly what had been taken away, and not one instrument stopped working. Which suggests that what these 10 reasons take apart is not the universe. It is a set of assumptions about the universe that turned out not to be holding anything up. Solidity, flow, depth, distance, objectivity, they were not the foundations. They were the handles we used to carry the thing around, and the thing is still here without them. The word real was doing much less work than it seemed to be doing when this list began, and finding that out costs nothing at all. The universe is exactly as it was 3 hours ago. Only the description has changed, and descriptions were always ours. Sleep well, and good night.